We'll continue on session.
Thank you. Can you hear me? Is it on? Higher.
That's right now.
Can you hear me? Is it working? Okay. Okay, so let's continue. So yesterday we started with some basics. We reviewed a little bit the geometry of ADS, and then we introduced embedding space and the form of correlation functions. So the last thing we said was we have bulk two-point function. Then by the isometry, this is going to be just a function of the chordal distance squared between these 2 points, and which we introduce this letter theta to denote it, and in Poincare coordinates it's given by combination. Okay, which is basically, you can think about it as kind of an invariant that we can build out of the the 2 points. And then one thing I wanted to tell you, still regarding a bit some kinematical aspect that we didn't cover yesterday, is so there is this concept of boundary operator expansion, okay, or boundary operator product expansion. So if we take some operator in the bulk of antidesitter, so tell me if you cannot see well or to write larger. Then one thing we can do, we briefly mentioned it yesterday, is that we consider the limit in which this guy approaches the conformal boundary. Okay, so we send it to infinity in space, if you wish, and it approaches this conformal boundary. And then a very important and useful concept is that we can rewrite then this insertion as an infinite sum of boundary operator insertions. Okay, so the expression looks something like this. So let me write it in Poincare coordinates, a little bit easier. So in Poincare coordinates, the boundary, you remember, is at z equals 0. So this takes the form of an asymptotic expansion for z going to 0. Okay, so it takes the form of a sum over primaries. So these are primary operators of the boundary. Primary means that they are annihilated by the generator of the special conformal transformations. Then you have some coefficient here. This is precisely the same coefficient. You remember there was a coefficient in the bulk boundary two-point function we said yesterday. Remember this object was completely fixed by symmetries up to a coefficient. Remember? So the same coefficient appears here, at least if we use a normalization in which the boundary operators are unit normalized. Okay, but okay, let's assume that. Let's assume that all the boundary operators are unit normalized. And then here we have this expansion, okay, where we have the boundary operator O hat of dimension delta. You see the power that appears is the zeta to the power delta in point x. And you have an infinite sum over descendants of this guy. So the infinite sum over descendants has coefficients which I don't know, I don't remember, but they are completely fixed by conformal symmetry, okay? And you can work them out with a little bit of work. Here I'm just using dimensional analysis. So there are going to be some derivatives of the operator. So these are what are called descendants of our primary hat. Okay, we have this infinite sum with coefficients which are fixed by symmetry. Okay, it's also difficult to actually, yes?
Are you assuming that the theory in the bulk is conformal, or is just the isometry of the spaces buying you the conformal technology?
No, yeah. The whole point of all this, why I like quantum field theory in ITS, is that we can use techniques of CFT also to describe massive quantum field theories. Okay, so all of this, what I'm using here is just the conformal symmetry acting on the boundary, which in the bulk is the isometry of the space. But this thing is going to exist for any massive quantum field theory as well. For any massive quantum field theory, if you put an operator here, you push to the boundary, you have this boundary operator expansion. Okay. So this is called boundary operator expansion. Or sometimes another name is bulk to boundary OP. Terminology is a bit, there are many names for the same thing. OP stands for operator product expansion. Okay, so there are two different names that are used.
Are you in a specific dimension here? Or?
No, this holds in any dimension.
I just remember that, I guess from holography that when you go to the boundary, there's that Z depends on there's a D minus.
No, well, I'm just saying that this is fixed by the dimension of the operator. So maybe maybe in a second we will discuss an example of the free scalar, which is maybe familiar from IDSCFT, and we can compare. Just let me mention that the relation to IDSCFT is that usually in IDSCFT we consider some Lagrangian in the bulk and we do computations perturbatively, right? So we mostly consider free theories or perturbative theories in anti-de Sitter, okay? And then typically what happens is that if this guy is an elementary field in the bulk of ADS, then you're going to have just one operator appearing in this, okay? And this is what in the language of holography we call the dual operator to the field, okay? It just means that if I'm doing free field, there is just one operator appearing, okay? This sometimes in the context of holography is called extrapolate dictionary, which means that you take the operator, the field in the bulk, and you push it to the boundary, okay? But this statement is more general. Any quantum field theory, any local operator can be composite or whatever. You don't need a Lagrangian or anything. If you push it to the boundary, you can prove that it has this expansion in boundary operators. Okay? Now,
one question, why only even powers of Z?
Okay, so here I'm assuming for simplicity that everything is scalar. Okay, so then there is nothing, no index that I can use to contract the derivatives. Okay, so in general, if you have a spin L operator in the bulk, the operators that can appear here are spin L, L minus 1, L minus 2, etc. Okay, and then there could be more complicated contractions. Okay, but yeah, if it is a scalar, there is nothing that you can contract the derivative with. Okay? You cannot explicitly put an x here because that would violate translations parallel to the boundary.
Such an expansion also exists in the boundary CFT.
Yeah. So in particular, so maybe I should have said that to the question before about CFT. So in particular, you can consider the special case in which the theory in the bulk is a conformal field theory. If you restrict to that particular case, this setup is completely isomorphic to boundary CFT. It becomes boundary CFT because you can just do a by rescaling. Okay. Yes, and cancel. The metric was like this. Okay. So suppose I put a CFT here. The CFT doesn't care about this factor. Okay, because it's a CFT, and so it becomes just boundary conformal field theory in that special case.
So, but this is the ADS isometries are crucial that this works with general Q.
It's crucial. It's crucial. So here I'm assuming that I'm really can couple my quantum field theory to the background, preserving the isometries. If somehow this doesn't work, then all I'm saying you can throw it. But in general, the expectation is that you're able to do it preserving the isometries if your theory is local and
Just
Yes.
I guess so. OP, the fact that OP is valid even in massive theories is
Yes.
just the fact that this is that you're putting it in ADS and then you have the same group as conformal group.
So just to be very explicit, in boundary CFT, there would be two OPs, right? There would be an OP in which you take the operator and you push it to the boundary, and there would also be an OP, maybe, I don't know if Shinan is gonna mention this or in his seminar, but there are also OPs in which you push operators close to each other in the bulk, okay? This thing we don't have here. This one doesn't exist if you have a massive quantum field theory in anti-de Sitter, okay? But this one exists. Okay. Now, so let's use this. I want to tell you a little bit how to use this to re-express this token function. Okay, so suppose now you apply to both operators. You push both operators to the boundary. Okay, there are no other questions. So we have this complicated function of zeta, of our invariant zeta. Now, for both of these, we plug in our expansion. What do we get? We get something like one sum and another sum over primaries. Okay, let's call this operator 1, this operator 2. They don't need to be the same bulk operator, they can be different. Okay, and there's going to be z to the power delta 1, z2 to the power delta 2, and there is going to be class descendants. Sorry, this is x1, this is x2, class descendants. Okay, but now one function on the boundary, it's diagonal. It's only non-zero if these are the same primaries. Okay, only within one conformal family I can have non-trivial two functions. So now this becomes instead of being two separate sums over primaries, becomes one sum over primaries. Okay, because of the I can just rewrite this as a sum over O hat boundary primaries of B1 O hat, B2 O hat. And then I'm going to have something like this, Z1, Z2 to the power delta, dimension of this primary. Then at the beginning, there is going to be the two-point function of my primary, which takes this form, right? But then there is going to be all the contributions of the descendants. Okay, so these are very boring to write down, but the coefficient, the important thing is that it's fixed by symmetry. Okay. So some smart and hardworking people were able to use the symmetry to completely fix this function. Okay, you can just work it out, and I can tell you what is the answer. So you can perform this sum over descendants.
So Lorenzo, maybe
Yes.
you can tell us what primaries and descendants are.
Yes. So what I mean is that we have the conformal group acting on the boundary, okay? And in particular, the generators are the dilatation operator, the translations, and then there is the rotations, and there is the other one which makes all the difference between having conformal symmetry or not, which is the special conformal generator, okay? And primary operators are defined by the property that if you act with this, the operator, let's say, inserted at the origin, you get 0, okay? And this is a very basic construction. When you build a representation of the conformal group, what you do is that you start from these guys, and then you act on them with P, okay? To generate the whole conformal family. So they are, in a sense, like kind of lowest weight, like how do you say it? So the thing you start with to build all the representation, okay? And P and K work as like raising and lowering operators in the conformal multiplet. Is that enough? Because yeah, unfortunately, I didn't have time to do a full review of CFT because it would take me too long. But okay, so now this whole function, I wanted to say that it can be fixed. It only depends on the dimension of the boundary primary operator. This is what we call a boundary conformal block. Or actually, sorry, I decided to call it in my notes bulk, 2 point. No, bulk, it doesn't make sense. I think I wanted to say boundary. Ah, yeah, sorry, I meant bulk 2 point function. Conformal block. In any case, it's a conformal block. People, when they say conformal block, they mean that they are summing over a tower of descendants, okay? So it can be different, slightly different conformal block depending on what correlation function you're considering. And it has this form. It depends on delta, and it depends on this invariant zeta, and it is zeta over L to the power minus delta times there is a simple hypergeometric function that appears. Plus 1 minus 4 L squared over zeta. Okay?
So d by 2.
Uh,
D by 2.
delta minus d by 2 plus 1/2, and this is 2 delta minus d plus 1. Okay, so turns out that, I mean, maybe some of you recognize this function. This is exactly the back-to-back propagator of a scalar field in anti-de Sitter, okay? With boundary condition that such that the dual operator is dimension delta, okay? This is not coincidence. I mean, we'll explain. It's just because basically this whole combination is due to the symmetry is annihilated. Sorry, it's an eigenvalue of the Casimir of the conformal group. And the Casimir of the conformal group is precisely the Laplacian, so that's why that's the relation to the.
And that's the whole sum that you've done there?
Yes, so if you had the full sum over the standards gives you this. This gives you this. So in practice, I can rewrite this as then just it's a sum over primaries of hat of B01 of hat, B02 of hat times this G point of zeta. Okay, that's the expansion that you get.
And maybe a silly question. So what so what happens if it's Z dependence? Z1, Z2?
It gets because this zeta, right? It recombines all of them in this invariant combination. Okay. Okay. Now let's do the simplest example, or actually just ask you to do it. I guide you. So if you want to.
Just one question. Are the bulk operators also labeled by some delta or no?
No, because there is no conformal symmetry in the bulk. So bulk operators are not, I mean, of course, there is a special case in which you can consider a CFT, but in general, they're not labeled by any dimension. So to make it concrete, the simplest example, and then simplicity is a bit subjective, but will be in free scalar. Let's say this guy. How do I call the mass? M, big M. Okay. So, for instance, what you can do to work it out, I will not do it in detail, but first of all, you can look at this correlation function. Okay. This is going to be now function of data. And I told you this is basically this function over here. Okay. So you can work it out by solving the equation for the propagator. And so we interpret it from the boundary P point of view. This is telling you that there is only one operator in the boundary of P. There is some special operator, let's call it phi hat, okay? In the context of holography, this is what I was saying before, we call the dual operator to the field. And it has dimension delta, okay? Which is related to the mass by the famous formula. Okay. Then, I mean, if you want to really work out this example, you can ask yourself what type of boundary spectrum you have, what are all the set of operators on the boundary, and what are the correlation functions, and full boundary spectrum. Here, I mean, I will not work it out completely for you, but the idea is that the theory is Gaussian, meaning that all the correlation functions are products, two-point functions, okay? So out of this operator phi hat, you can construct all the other operators by simply doing products, okay? And all the correlation functions are gonna factorize due to the fact that the theory is free, okay? So this is what sometimes is called generalized free theory or mean field theory. It has many names, but that's what it means. It's a special kind of conformal field theory in which all the correlation functions are simple in this sense. Just comments. The comment is that the way if you want to compute that function and show that it is hypergeometric, you need to solve this equation, right? And it's convenient to parameterize like this. And then you find two solutions. Let's call it G delta plus minus, okay? Which are associated to the two solutions here, right? Let's say that delta plus is the bigger one, okay? And what distinguishes them is the boundary condition that you impose on this solution. In order to completely fix here the solution, you also need to impose a boundary condition at large zeta. So this is an additional input that you need to put in this theory. When you want to solve your scalar field in ADS, you need to input also this. And these are the two possible boundary conditions, okay? Now, this is, I wanted to stress it because it's an example of something which is that in order to completely define the set of all the boundary correlation functions for this quantum field theory, you often, actually always, need to make also some discrete choice of boundary condition. Okay, so it's not like just telling you the bulk Lagrange and it's enough. Okay, I need to tell you what boundary condition to specify, and here, depending on whether I choose this boundary condition with plus or minus, I'm going to have a different set of boundary correlation functions. Okay. Another reason why I wanted to mention this, that using this function g, we can do a nice construction. Are there questions? The example is
Theta is the distance square.
yes. This is always the chordal. This invariant that we have. That was always the chordal distance square.
So are you saying that you're getting two different
So-
CFDs depending on the boundary?
Yes.
Different theories of principle.
Different theories. Yes.
In this case, it's free, so there's not much.
Right. Yes, but I'm gonna get two different set of boundary correlators depending on the boundary condition.
Again, it's not like any CFD where you have the source and the response. Like, I mean, where.
Yeah, I mean, this is also familiar also from holography. Also in holography, you need to specify boundary conditions.
But one of them is taken to be they have different interpretations, let's say, in the dual theory, right? One is the,
Yeah, but sometimes you have two choices. No? Sometimes you can swap between what you call source and what you call operator. That's what I'm saying. There are two choices. Now, one thing that I wanted to describe that.
In PFD, I mean, in field theory general,
Huh?
there is this power law fall off and there is exponential fall off, which can be connected to the absolute persons of a mass.
Yes.
So the same idea of mentioning.
No, it doesn't apply here in the sense that in ADS, so precisely when we say that it's an IR regulator, what we mean is that it's always akin to exponential cutoff, fall off. So this power of delta minus delta, if you express it in terms of the geodesic distance from a point in bulk, let's say you fix some point, you call it the origin, and you look at that, this is always an exponential fall off. So even if you have massless fields in anti-de Sitter, it always falls off exponentially at the boundary. So in fact, you don't see a crucial difference between putting in the behavior of correlation functions at large, so you don't see a crucial difference between massless or massive case, which is related to the fact that you don't enhance the symmetry. If you have a conformal field theory in ADS background, the symmetry is the same as a massive quantum field theory in ADS background. Okay. What I wanted to say is that there is a convenient way to express. There is a convenient integral representation of Arctic function, which is by expanding in eigenfunctions of the Laplacian. Okay, we're calling the delta the propagator of the scalar. Okay, we can build this function, usually called omega. It is a conventional factor that we put in front. So we can take this propagator with the dimensions d over 2 plus a nu, and subtract the propagator with dimension d over 2 minus a nu. So considering this combination, what it does is that, the propagator is singular at coincident points, right? Because it needs to give you a delta function when you act with the box. But if you consider this combination, the singularity at coincident points cancels. So this function is regular at z going to 0, okay? And also, when you act with a box on this, the delta functions given by these two guys are going to cancel, okay? And you're going to get precisely the same mass squared from this and from this. So this is actually an eigenfunction of the Laplacian. So if you act on this with minus box, get this combination, d squared over 4 plus 2 squared omega. Okay. Now nu, you can take it be a real positive number, and this gives you all the set of the eigenvalues of the Laplacian in ADS. So this is a complete set of the eigenfunctions. And they satisfy, so if you, it's a complete set, like they're, this is, I mean, the L2 norm. So you take the product, you integrate over ADS, you just get nu plus nu prime. Here I'm extending nu to be a real number, just as convenient to take also no, but this function is completely symmetric. Okay, so if I use this, I can do kind of a Fourier transform, expanding in this object. So the correlation function I had before, which was a function of zeta, okay, this was back to one function. I can now write it in an expansion in this basis. So this is kind of a Fourier transform. So I trade my function of zeta, I trade it with a function of nu. Okay, and there is an inversion formula. So you can write this f tilde as an integral in d zeta with some kinematical, some geometric factor times omega nu of zeta times your f of zeta. Okay, so there is an inversion formula. Something like the Fourier transform. And why is this representation useful? So it is useful because now all the information is here, and this function of nu also repackages very efficiently this boundary operator expansion that we discussed before. So
why has delta become imaginary now? I mean, this I mu.
Well, I didn't explain that in detail, but you know, if you want to have something that is an eigenvalue of the Laplacian, then you need to consider this combination of g of delta minus g of d minus delta. Okay, so imagine here you put delta, and here you put d minus delta. Okay, now you need to find the sweet spot such that both of these things are normalizable at the moment. The best thing you can do is to take delta to be d over 2 plus an imaginary number. So this gives you something that is at least delta function normalizable. Okay.
Sorry, I don't understand this part. You started with nu greater than this.
Yeah, this is simply a formal thing that, I mean, the correct spectrum of the Laplacian is labeled by nu positive. It's just I find it convenient to extend to all real values of nu, and I'm doing this by taking this to be a symmetric function under nu goes to minus nu. Also, this Fourier transform is going to be symmetric under nu goes to minus nu, but it's just a convenience. There's nothing deep about it.
And this transformation has a name?
I mean, sometimes it's called spectral representation. It goes under different names in different, but okay, yeah, we like to call it spectral representation. So what do I want to tell you? I want to tell you that, you know, if you have this guy, how can you recover from this, the boundary operator? Suppose somebody hands you this function f tilde, okay? What you can do is that you can take this integral in the complex nu plane. You're integrating over here. And then simply what happens is that this function f tilde is going to have a set of poles. Okay. Everything is going to be symmetric because I told you that I just do everything symmetrically. Nu goes to minus nu. Okay, everything is symmetric in this plane. And then what you do is that you need to take your omega and rewrite it as g minus g of d over 2 minus I nu. It turns out that one of these two pieces can be closed down in the complex plane. The other piece can be closed up the complex plane. So you're going to close with an arc here with the g of d over 2 minus I nu. You're going to close with an arc in the lower half plane. The arc is not very visible. With g of d over 2 plus I nu. Then you pick the poles and you recover the boundary operator product expansion. So the crucial point here is that this, like the poles of f tilde are correspondence with operator or dimension of primaries appearing in boundary operator product expansion. Okay, so as an example, suppose you again do it for the free scalar propagator. Okay, you can apply this formalism to it. What functions you're going to get? You get this beautiful function here, 1 over nu squared plus delta minus d over 2 squared omega nu. Okay, so you get this simple thing, which has only one pole in the upper half plane and one pole in the lower half plane, because we said that there is only one operator appearing in that case, in the boundary operator product expansion. And look at this function here, this g tilde of nu that we got. It's remarkably similar to Euclidean propagator in momentum space, right? In flat space. It's very similar to 1 over p squared plus m squared, right? And indeed, one can show that this function, if you take the flat space limit, just becomes the Fourier transform of the Euclidean correlation function. Okay. Now, the last bit I want to tell you before giving you a more sophisticated example is a very nice property of this representation, which you might already anticipate. A very nice property is that since it's analog to Fourier transform, this thing behaves well under convolution. Okay, so this is useful to know. What am I saying? I'm saying that. Can I raise here? Or there are questions? Behaves well under convolution. Suppose you're given 1, 2, and you made a lot of effort, and you managed to compute f tilde 1, 2, no. And then the same with another correlation function, another 2 operators. Okay. Now, the good news is that if you want to compute the convolution, so you integrate over point x of O1, x1, O2, x times O3 x, O4, let's call it x4. Okay, so you integrate these 2 point functions, the product of these 2 point functions in a common point. So this, again, now this is just a function of x1 and x2. Okay, so again, I can do the spectral representation for this guy. Okay, and the claim is that, so let's give it another name. Let's call it H, okay, just to give it another name. The claim is that if I do spectral representation of this function H, it's just going to be the product. Okay, exactly like you would expect for a Fourier transform. It behaves well under convolutions. Okay, this simplifies a lot of calculations, and I'm going to use it in a second. Okay.
So you've got an H of x1 and x2, or
X1 and X4. Yes, sorry. Sorry.
Is this H again a 2-point function or?
Yes, yes. I mean, this thing, you see, since I'm integrating two scalar two-point functions in a common point, it's going to have the same property, the same symmetry properties.
Are you assuming all of them are identical operators? Same operators?
No. This can be any operators. I mean, I'm just saying you take a two-point function, you take another two-point function, you do a product, and you integrate over a common point. These are precisely the same symmetry properties of a two-point function.
But it won't depend on what operator you're using.
I mean, of course, this function is going to depend on what operators I'm using, but also this expression, you see, it contains the information of which operators I'm using, no? Thanks F12, thanks F2.
Oh, I see. Okay.
Yeah.
But then, I mean, for example, I can replace 2 and 3 by any other thing, and it would still remain. H would still be H of x1, x4.
The fact that this depends only on these 2 points, it doesn't depend on which operator you put here. This precise form of this function depends a lot on which operators you put here.
Yeah, I'm saying that I can get it's non-unique. I can just replace 2, 3 by any other operators, and I will get a lot of different representations.
Yeah, this function is labeled by the whole 4 operators. This depends on which operator is in 1, which operator is in 2, which operator is in 3, and which operator is in 4. I'm just saying that kinematically, it just depends on the points x1 and
Okay, sorry. Yeah, okay, I understand.
Okay, so maybe finally I can deliver on my promise of discussing some dynamics in the remaining. Yes? Mm-hmm.
I mean, it's not f squared, right? But give back f.
Well, if you do, so how does it work with the propagator? You're asking if I do 2 back-to-back propagators. So I take these 2 back-to-back propagators and I integrate over this point. But what is this? You can imagine it as you put a vertex phi squared, right, in your theory, and you're computing a mass insertion. And indeed, what I'm saying is that the spectral representation of this, after I integrate over this point, so I do the integral over this point, is going to be 1 over nu squared plus delta minus d over 2 squared, everything squared, okay? Which is precisely the derivative with respect to the mass of a propagator. You see, this object here, in which you connect 2 propagators and you integrate over a common point, is the derivative with respect to the mass of a propagator. This is precisely what this formula is telling you. Do you agree?
Not just the propagator itself?
No, it's not the propagator itself. I mean, if you take 2 propagators and you integrate over this common point, you obtain the mass derivative of a propagator, right? The derivative with respect to m squared. And this is indeed the derivative with respect to m squared. I mean, okay, you have to rewrite it in terms of m squared. Okay, so I want to discuss this example. Of, let's consider an example of a interacting theory, which is, let's see, I think I want to start directly from this. Let's discuss the one sigma model in this. Okay. So first I will tell you what the theory is, and then I will say what is the interesting question to ask. Okay. Okay, let's consider this theory. I like to write it like this. So what is this? This is a theory that describes n scalar fields. I goes from 1 to n, okay, two dimensions, and sigma is a Lagrange multiplier that enforces the constraint that phi I is to be equal to, I mean, this n is just a normalization, and this g squared is the coupling, okay, of the theory. And so what it's telling us is that the scalars need to live on a sphere, okay? The parameterized sphere. The scalar product is
It's not the same as G in square root of G.
oh, sorry, I'm using the same letter for two different things. That's terrible. Let's call the metric of ADS capital G. Sorry. Sorry. So they are leaving the phi's parameterize a sphere S n minus 1. Correct? Yes, Sn minus 1. Now, just as short reminder of what we know about this theory in general, like with no reference to ADS. Okay, so this theory is an example. People love to use it as a toy model of strongly coupled gauge theories, for instance, in 4 dimensions. Because what is the similarity? The similarity is that anybody who looks at this Lagrangian would guess that this describes some Goldstone bosons, right? Because I just have some scalars that parameterize a sphere, so perhaps they're massless and I can move them around the sphere. But then it was discovered in the 70s, I guess, that this is wrong. And actually, this theory, since it's asymptotically free and it flows to strong coupling in the IR, what happens is that it actually develops a mass gap. Okay, so the ON symmetry, so actual dynamics that we know in R2, let's say, this theory has a mass gap, and the ON symmetry is unbroken. Okay, this is related to the statement that there are no Goldstone bosons in 2 dimensions. Okay, so this wanted to be a theory of Goldstone bosons, but it cannot be a theory of Goldstone bosons, and so there are actually massive excitations that are realizing the symmetry linearly. And okay, so if you compute the beta function of this coupling G, you see that it's like minus G cube in my normalization over 4 pi. And this is actually exact if you do a large n expansion, in the sense that at leading order a large n is just this one loop that contributes to the beta function. Okay, so a nice thing of this is that it admits a large n expansion. It's exactly solvable. In large n limit. Okay. Now, what is the nice question to ask in ADS? So in ADS, you see, there is a little bit of a puzzle that one might face when studying this theory, because see, this theory is asymptotically free. So when you go to the UV at very small distances, it does seem like you have free scalars, free massless scalars, right? It's only in the IR that it develops this mass gap, and the physics becomes very different. So now, if we are in ADS2, we can start by dimensional transmutation. Here we have dimensional transmutation. There is some lambda G, okay, some dynamically generated scale. And now in ADS2, we can consider physics as a function of this lambda G times L. Okay? Now I'm saying that when lambda G L is very, very small, then indeed it should be reliable. Lagrangian should be reliable. Okay? And indeed, it is possible perturbatively when ADS is very small, it is possible to impose a boundary condition in ADS to my scalar fields that breaks the symmetry. This boundary condition exists in ADS. It doesn't exist in flat space. In flat space, you cannot break the symmetry. In ADS, you can.
Sorry, how do you define a reliable energy? What's
No, sorry, I just meant that you can do perturbation theory. So it's a weird way to say that perturbation theory is okay. I said it in a weird way. So what happens here is that you can impose a boundary condition like this. So the field approaches a constant, then the fluctuation comes with the power of z. Okay, so this is like the boundary condition that you have for a massless field in ADS. Just the boundary behavior of massless field. And this power z to the power 1 is because I solved delta minus 1 equals 0. Okay? So that's why I get this power 1. So what I'm saying is that there is a very, very well-defined boundary condition which just I fix the value of my scalar, and then indeed I see these fluctuations which are Goldstone bosons, if you want. Okay? So this exists in ADS. And so in particular, something that is extremely, I just want to tell you that is very analogous to Goldstone theorem in flat space is that now you can take the ON current in the bulk, okay? And then if you study the Z component of the current, so here I'm now in ADS2, so this coordinate is Z as usual, and I have only one boundary coordinate, which is X. So to see that the symmetry is broken, you just look at, in ADS, you look at the flux of the current, okay? And with this boundary condition that I mentioned here, you can indeed check that this current has a flux, okay, at the boundary. Flux goes like this. Like this bev AI times OH J antisymmetrized. So when currents are antisymmetric in the indices I and J, well, you see there is a non-zero flux, which is a 3DS arrangement of one-term symmetry breaking. Okay. Now, and the fact that this operator OI has dimension 1 is like protected by the symmetry. In the same way that the fact that the Goldstone boson is massless in flat space is protected by the symmetry. Okay. Now, what is the puzzle? The puzzle is, let me draw something here. I don't have much time left, but I should be able to tell you.
Is this an infinite?
Punchline. Sorry?
This infinite n?
So far I didn't use much infinite large n. These considerations I'm doing are general also for finite n, but at some point I will want to use large n. So what I'm saying is that now imagine you consider this theory as a function of lambda GL. What I'm saying is that here, when this is very small, I can have one-term symmetry breaking, okay? there is a boundary condition that gives me these Goldstone bosons. On the other hand, here, when lambda GL is very large, I need to approach it to reproduce flat space. Okay, so in particular here, there should not be any Goldstone boson. The symmetry should be realized linearly, and everything should have a mass. Okay, so in particular, all the boundary dimensions should scale like the mass gap times L. So they should all go to infinity. They should shoot linearly with L as I go to very large lambda L. But there is a puzzle of how to connect these two. Puzzle is what's here in between. Okay, and so at large n, you can actually see, do an explicit computation to see what happens. And what happens is that, how do I explain that?
Sorry, question.
Yes.
If you look at other directions, flux is 0 in other directions.
Well, the interesting question to ask to test spontaneous symmetry breaking is just the flux
Is
perpendicular, like the flux at the boundary. That's what means, because if this is non-zero, it means that your boundary is breaking the symmetry.
And can we say something about the conserved charge in this system?
The conserved charge, What-
Charge conserved or?
well, basically the fact that there is this flux tells you that the charge can deposit at the boundary. Okay, so that's the statement that infinity in your space is breaking the symmetry. That's spontaneous symmetry breaking. Let me see how I can get to the punchline. Okay, so in order to understand what's going on, we needed to do computation. And the computation you can do on Largan. So, let's check what happens at Largan. And what happens at Largan is that you discover it by studying the correlation function of this Lagrange multiplier field. Okay? And the tool to do the computation is precisely this integral representation that we saw before. Okay? To compute this function here. And okay, if I had more time, I would explain to you some details of how we compute it, but now I don't have time to tell you. But it's very crucial, this property that we said that it behaves well under convolution, right? Because it's basically, if you're familiar with Largan techniques, in order to compute this correlation function, it's typically resum bubble diagrams. And the fact that this behaves well under convolution allows you to resum bubble diagrams as you would do in flat space. So we can compute this object. And then by computing this object, what did we see? We saw that at lambda GL order 1, a boundary operator, singlet of point symmetry becomes marginal. Okay, so the boundary dimension becomes 1. So marginal operator means that dimension is exactly the same as the space-time dimension. So in this case, this is a CFT1. So marginal operator is of dimension 1. Okay. So what happens when a singlet operator becomes marginal? You see, when you have a continuous family of CFTs, and at some point some operator hits marginality, becomes marginal, then you need to worry. You need to worry because this operator can start running if it is marginal. So let's call this operator that became marginal how do we call it? Let's call it O hat with a very original name. Okay. Then you need to ask yourself what happens at this point when the operator becomes marginal. What happens if I add it to my boundary Lagrange? Okay. And you can go ahead and compute this beta function of this coupling. Okay. And you discover that there are two terms. You see, the fact that it's marginal means that there cannot be a linear term in Y. It starts quadratic in this coupling Y. But then there is also, crucially, a contribution from the bulk. So if you displace yourself a little bit from this critical value, let's say lambda GL critical minus lambda GL. Say that I'm working perturbatively in this difference. I'm moving a little bit away from the critical point. And then you find that there is no, like, past the critical point, there is no real zero. For Y. Okay? So you cannot satisfy the beta function of this coupling. So that's the way you basically lose the Goldstone bosons as you approach flat space. What happens is that this boundary condition that has Goldstone bosons at some point stops existing as an allowed boundary condition that is unitary and preserves the DS isometries. Okay? So imposing that this beta function is zero is important because otherwise I break the isometries. But there is a clash between the requirement of the isometries, and this needs to be zero, and the requirement that my theory is unitary, which means that the zero of the beta function must be a real value of the coupling. So this quadratic polynomial stops having a real zero past the critical point. So basically what happens is that the way this is completed.
Sorry, what is Y? What is Y?
Y is the coupling. So I did a computation, right? And I found out that an operator is marginal. So then I need to ask myself, okay, this is marginal, then what happens if I add it to the Lagrangian, right? So I'm adding it to the Lagrangian with some coupling Y, and I'm studying the beta function of this Y. So the Y is precisely the coupling associated to this operator. And I find this quadratic polynomial, and I'm playing this quadratic polynomial only has a solution before I arrive to this critical point. So here there is a real solution for beta of Y equals 0. That's precisely my boundary condition with Goldstone bosons. But past this point, there is no real solution. Okay? So my boundary condition stops existing and I transition to the gapped boundary condition. So after this point, there is only the boundary condition with a mass gap. And that's how I recover the mass gap in flat space. Okay?
You mentioned about something about Goldstone bosons.
So yeah, in this, the boundary condition has Goldstone bosons. I just said that the Goldstone bosons only exist up to intermediate value of the coupling, and then they disappear. They become a complex boundary condition. So this was a way in which we could see in a sense, the emergence of the mass gap by moving this parameter, you see? We asked ourselves, how come in flat space we have the mass gap? And then with coupling, we see Goldstone bosons. Well, the answer is that the Goldstone bosons at some point stop existing because the boundary condition becomes complex.
The symmetry is restored.
The symmetry is restored. Yes. Yes, I think I can stop here.
Okay, let's thank Lorenzo. Before the coffee break, any questions? Yes.
I missed this part.
Yes.
How was lambda G determined in the bulk in this sigma model?
How I come
The IR cutoff, the lambda G.
Lambda G? So this is just the usual. So you have a one loop. What I mean is just a dynamically generated scale induced by this beta function.
See.
You see, you're familiar with the fact that maybe that if you have the one loop beta count it is negative, then you run some argument and you find an RG invariant scale, and I call it lambda G. Okay, I'm just saying that naively it looks like you have a dimensionless coupling, but actually you have a scale in this theory, right? In flat space, this is the mass gap, but now in ADS I have this dimensionless combination.
The one model in 1+1 in flat space was solved by the Zamologikovs,
Yes,
any n, and
yes.
is it not possible to do that for the ADS version?
Well, it will be very nice, but I don't know how to import these integrability techniques to ADS2. Yeah, that would be. I think people tried. I didn't try so much personally myself, but I've heard that. I mean, we discussed there is also some no-go theorem that people proved for integrability for quantum field theory in ADS2. Of course, this no-go theorem it's always like it depends on what precise definition you take for integrability in ADS2, which is not immediately clear. That I mean, you can maybe change a bit and you find that there is an example, but at the moment I don't know how to solve this theory using integrability for finite n. I have to mention, maybe a good thing to mention is that there is another non-perturbative tool which I actually want to use in this setup, which can be used for finite n, and it is the numerical conformal bootstrap. Okay, so another nice aspect of quantum field theory in ADS is that you can also use the numerical conformal bootstrap on the boundary correlators, and that can be used also for finite n, of course.
So, and how did large n play a role?
Large n played a role because it allowed me to compute this fund. So you see, yeah, unfortunately, I didn't have time to go into the details of that, but this object here, the reason why I could compute it and I could see that at some particular value of lambda G, there is an operator hitting marginality is because I used large n. Otherwise, I wouldn't know how to compute this.
Maybe also a bit more general, but when you go to ADS from a class, it makes sense to have a conformal things with the scalars, or it doesn't affect much, but just a shift in the mass.
No. Well, usually what we do is that we call little m squared something that contains both the flat space mass and the conformal coupling. Yes.
So that could theory do not change anything.
Yeah, no, we just at the end of the day, there is no way to distinguish. R is just a number, right? I mean ADS. So yes, so it's just I just take the operator phi squared and whatever is the coefficient there, I call it m squared.
Any final questions? Otherwise, we continue at 11. The second or the final lecture is by others. Sure.
No.
Let me try. So,
Okay, I think we can start again. So we'll have Lorenzo's last lecture. I guess it's more of a research talk now.
yes.
On the topic that we both wondering about first, is the idiot's perspective. Please.
Thank you very much. So, yes, I'm sorry that this morning I monopolized your time. Let's see. Okay, so yes, in this last, this is gonna be more like about my research, and I'm gonna tell you about how to use the idea that we discussed in the lectures to try to say something about confinement from the point of view of anti-de Sitter space. Okay.
So just hold on 1 second.
Yes.
No, sorry.
Okay.
Sorry.
So the setup is that we're going to consider, to be concrete, let's say SUNC gauge theory, and we can also add some flavors, let's say NF flavors of Dirac fermions in the fundamental, or we also consider the case of scalar matter. And I'm going to take this theory and I'm going to put it on the space I've been talking about all this time, which is rigid the ground of anti-de Sitter space in 4 dimensions, okay? And I think I can be now a bit fast on the motivations because it was a topic of the previous lectures, but just to remind you, what's the idea? The idea is that this dates back from this old paper by Callan and Wilczek. They were the first one to consider gauge theories in a hyperbolic space back in 1990. And the idea is that now we gain this dimensionless parameter that we've been talking about. Oh, is that the pointer? Doesn't work. Okay, it doesn't matter. And then we have a large space-time symmetry. And also we can consider correlation function of boundary operators, okay? Now this lambda here, of course, is the dynamically generated scale of the gauge theory, okay? Maybe I didn't stress this in my class, but equivalently, you can also think of the dimensionless coupling as when you have this running coupling, right? You can also take the gauge coupling and just normalize it at the scale, which is fixed by the radius of ADS. That's analogous. It's another way to say that you have a dimensionless parameter. And yes, so these correlation functions of boundary operators are what we call the boundary CFT. And the data, thank you. The data of this boundary CFT are, as we stressed a bit in the lectures, not fixed uniquely by they depend certainly on this dimensionless parameter. So for every value of lambda L, I'm going to have different operator dimensions, correlation functions, but this doesn't fix uniquely because there is also a choice of boundary condition that I need to make, okay? Depending on this discrete choice of boundary condition, I might have different functions of this coupling, okay? So these are what the boundary CFT depends on. Bulk couplings and boundary conditions. Please stop me at any point if something is not clear. So now, yes, so the idea is to have kind of a CFT approach to the dynamics of the gauge theories. And here is the cartoon of ADS that is small and then it becomes big as measured by the dynamically generated scale. And so you first start, I don't want to spoiler. So you first start by studying the theory at weak coupling, right? When ADS is very small, and you start asking yourself simple questions like what are the possible boundary conditions? And then you start studying the property of the boundary CFT of weak coupling, like what are the symmetries? What are what we call mean field theory limits, which is this limit in which everything is computed just by weak contractions, okay? What type of mean field theory you have? what is the light spectrum of operators in this weakly coupled limit. And you can also do some perturbative computation of the data, okay? So this you can really nail down. Of course, the most interesting thing is to understand the strong coupling limit, which I want to stress that is also the flat space limit, right? So that's really what we want to solve, right? We want to solve what happens when the radius is large, which is our gauge theory in flat space. And so if you want to connect to this, okay, you cannot all your life just spend studying the theoretical coupling. At some point you want to go here. So you need to try to understand out of all these possible boundary conditions, which ones survive in this limit, okay? Which ones, maybe some of them disappear, some of them keep existing. And if you find some boundary conditions that continuously extrapolate to flat space, then you can try to work to recover the flat space data from the data of this boundary CFT. For instance, what do I mean by flat space data? I mean the mass of asymptotic states or couplings, okay? So these are all encoded in some way in this boundary CFT data, okay? I should be able to extract it from the flat space limit. So that's really the goal. But of course, the hard thing is to go from weak coupling to strong coupling. So here, I want to stress once again that there is a very important role that can be played by the conformal bootstrap, okay? That's an aspect why we like to study quantum filtering in ADS, is that given the symmetry, we can use the power of conformal symmetry to constrain these boundary correlators. And recently, we did have a paper in which we applied this kind of logic precisely for young means in ADS4, okay? And we managed to use the numerical conformal bootstrap to rigorously rule out some possibilities for what can happen in here in the middle, okay? So this was some progress. We are not yet able to use the numerical conformal bootstrap to compute the mass of the blue balls in means, okay? We are not there, but okay, there is some progress in this extrapolation using the conformal bootstrap. But this is not, my talk will not be mostly on this, as I just mentioned it. I will talk about something which is more about studying the spectrum of weak coupling. So let me start by in the weak coupling end, explain to you what are the simplest possible boundary conditions that we can impose. And then I will formulate a sharp problem that exists in this extrapolation and what are some possible solutions. Yes?
So by conformal set there,
yeah.
Mind the process that you okay.
Right. Yeah. So what we did is that we studied the Dirichlet boundary condition. We studied 4 point functions of currents in 3-dimensional CFT, and we imposed the symmetry on that. Okay, so this is probably the most famous boundary condition for a gauge theory in ADS, right? Which is that your bulk gauge field approaches with a power of z an operator which is a conserved current at the boundary, okay? So this is the one that is typically used in the context of holography, and that's the basis of the usual claim that a gauge symmetry in the bulk gives you a global symmetry at the boundary. That's what it means, that if you impose the Dirichlet boundary condition, you get a current. So this, when you impose this Dirichlet boundary condition on the gauge fields, you get a continuous global symmetry, which is precisely the color group SU and C, and with associated current J. On top of that, if you have matter, you also have a flavor symmetry, but this flavor symmetry is not doesn't have a current associated to it at the boundary, because you see the current sits in the bulk, okay? But still, you can have, it still organizes the correlation functions of boundary operators. It still gives you selection rules. It just doesn't have a current at the boundary. So what is the set of boundary correlators at weak coupling? It's basically just the mean field theory of this current. It means that all the correlation functions are going to be correlation functions of many of these J's that you can compute with weak contractions, okay? And then you're going to have other operators are going to be products of this J. You can have JJ operator, JJJ operator, and so on and so forth. That's the full list of operators that you have with coupling. And of course, there is also the operators coming from the matter. So if you have your fermions, they're going to give you some operator at the boundary. Let's call it psi hat. And you're going to have psi hat squared. Okay, so it's very simple, the spectrum by decoupling. In particular, the lightest operators are this current here, which is conserved, so it has dimension 2. And then there are operators coming from the matter fields. These are the lightest ones. The operators coming from the matter field, they are both charged under the color symmetry, and they're charged under the flavor symmetry. And they will have some scaling dimensions that depend on the mass, on the choice of the mass for these fields. Okay? And then, of course, I also have double and multitrace. I mean, this multitrace is a bit of a misnomer. I just mean products of these fields, products of these operators in various representations of SUNC, of the flavor symmetry. So that's one possibility. Another possibility, which is a bit less studied, but certainly exists, is to impose a Neumann boundary condition for the gauge field in ATS. So the Neumann boundary condition, instead, the behavior is like a constant. It doesn't go to 0, the field at the boundary. And what actually happens here is that you introduce a 3-dimensional gauge field at the boundary of your space. Okay, so this operator here is actually not gauge invariant operator. It's like it plays the role of a 3-dimensional gauge field. So this is an allowed boundary condition, and this means that you only have flavor symmetry now at the boundary because the SUNC is still gauged at the boundary of ADS. So you don't have any more this global symmetry. Okay? So it's a bit more complicated here, the situation, because you only have singlets of this SUNC. Now, the boundary operators can only be singlets. So, for instance, now when we are at strictly 0 coupling, our boundary conformal field theory is going to be, you can construct this field strength out of your 3-dimensional gauge field. And you can sort of build a mean field theory out of this F and the matter fields, but importantly, you need to restrict to singlet sector of this SUNC, okay? So you can form products, but you always need to be careful to contract all the SUNC indices because this is now a gauge symmetry, okay? And now the light spectrum is a bit less obvious because this F by itself or the matter operators by themselves, they're not gauge invariant. So these are not anymore light operators that exist. So for instance, the lightest one would be something like trace of F squared. Trace of F squared is an operator that exists at the boundary. And it has dimension 4 at weak coupling, okay? But okay, so this is what happens when you study the theory at small ADS radius. And now you can ask, okay, but what do I expect at strong coupling, okay? Well, at strong coupling, we have an expectation that the theory should exhibit color confinement, which means that the asymptotic states are neutral under this SUNC symmetry, okay? And now this immediately tells you there is some clash with this Dirichlet boundary condition, right? The Dirichlet boundary condition, we said that it has this SUNC symmetry at the boundary. This was observed in this paper in 2012 by these authors. And so their observation is that if I impose the Dirichlet boundary condition at small ADS, there must be a discontinuity. There must be a discontinuity as I increase the radius. So there is a transition between a deconfined phase when the radius is small, meaning I call it deconfined because I have this color symmetry, like you can imagine it as a boundary condition with gluons, but then at some point the gluons must disappear and I need to transition to the confined boundary condition. Okay, so you expect a discontinuity with Dirichlet. On the other hand, if you instead impose Neumann boundary condition, you see already at weak coupling, we only have singlets. So in this case, there is no reason to expect any discontinuity. And you can hope that this boundary condition is continuous, okay? So that's the picture. Of course, conjectural. We don't know yet that this is continuous, but that's a reasonable expectation. Okay, just some technical observation before we move on is that if you consider the theory without matter, there is another thing that tells you that Dirichlet must disappear, which is the expectation that there should be a mass gap, right? So the theory should be gapped, and if you have a current, certainly if the boundary condition with a conserved current would exist all the way to the flat space limit, this would give rise to a massless particle. So it would be in contradiction with the existence of the mass gap. So this is another way to say that the Dirichlet boundary condition cannot extrapolate continuously. Another observation is that I stressed before the definition of color confinement, right? I phrase confinement using the notion of that no asymptotic states should be charged under SUNC, okay? There is various notions of confinement that one can think of. Another notion that is very important is the existence of a linearly rising potential between quarks. And if I'm going to consider theories with fundamental matter, this is not really available to me because the strings can break because of and create particle-antiparticle pairs. So that's why I stressed the definition in terms of asymptotic states. And I also want to say that this particular definition, usually in flat space, what we do is that we rephrase it in terms of expectation values of the Wilson line operators having area law when the Wilson loop is very large. And this is not immediate to import to anti-de Sitter because if you take a very large circle in anti-de Sitter, the area and the perimeter scale in the same way, okay? So you should do something a little bit more sophisticated. So it's possible, but it has not been studied very much how to import this condition to anti-de Sitter. The right condition is something like you should ask yourself whether Wilson loops are allowed to end on the boundary or not. But okay, this is just a parenthetical comment. For the purpose of this talk, we are going to consider the definition of confinement as color confinement, okay? Now, given what I said so far, one can be very ambitious and set these two tasks. That would be very nice. So one task would be to be able to show that the only boundary conditions that extrapolate to strong coupling or large LDS are the ones in which there is no SUNC symmetry on the boundary, okay? But if one would be strong enough to do this, then basically you prove confinement, okay? But it is, of course, very hard. But it's at least nice that we can formulate in this way. Like, okay, we have a way to formulate it from the point of view of this limit from small to large ADS. But the question of proving confinement from this point of view would be the question of proving that the only boundary conditions that can survive are the ones that don't have this symmetry. This will become more clear when I go on, but we saw an example in the previous lecture that there was some boundary condition that existed when ADS is small, and then at some point it became complex. It stopped existing. So
if you pose a boundary condition, the fields become complex.
Or some coupling becomes complex, more precisely. So yes, there is an important concept that as a function of this lambda L, what the set of all possible boundary conditions might change. Okay, so as you change the coupling, you change the radius of ADS. What boundary conditions are available to you depends. Okay, so it could be that even though at weak coupling, we see that there is this Dirichlet and no boundary condition, and maybe there are infinitely many more, who knows? But you would like to prove that when lambda L is large, the only allowed boundary conditions are the ones that don't have this symmetry, this color symmetry. Okay? Another interesting task perhaps more practical would be to say, okay, Neumann is continuous, let me use it. And with the power of conformal symmetry, I'm going to compute the scaling dimensions, extrapolate to large radius, and compute the mass of the blue balls or some other observable that I care about in the gauge theory. So that's another thing that is very nice. It has been studied a little bit in this recent paper, restricted to the observables that are related to the confining string. Okay, so they studied a bit confining string for Young Mills in the context of ADS.
That was such an extrapolation work.
Well, what, for instance, was done here is that they had in both limits, both the limit of lambda L large and limit of lambda L small, they had some computational tool. So in the limit of large lambda L, they were using the fact that the string, the confining string has a controllable effective field theory expansion. So they were computing some observable in the limit of large lambda. They were computing some observable in the limit of small lambda, and they were seeing that there is a reasonable way to match the two ends. Okay, so it was not like they didn't do full computation at all values of the coupling. You need to use some non-perturbative tool. So either you, if you really want to do this extrapolation, so either you can try to use in some clever way the conformal bootstrap, or another thing that has been done is you can consider, for instance, you can ask also these questions in supersymmetric versions of the theory, and then you can try to do the computations exactly. You need to use some non-perturbative tools to really do this extrapolation. But I want to say that the fact that you have conformal symmetry does help you. So there is a more humble first step that you can try do. Okay, maybe proving confinement is a little bit too much, but for instance, it would be very nice to argue that at least the Dirichlet boundary condition disappears when we make the coupling large. I think this would go, in my opinion, a long way in understanding why the Lagrangian, in a sense, is giving us wrong information, right? Because the Dirichlet boundary condition is the one that tells you that you have massless gluons, but then you see that at some point something goes wrong with it. Okay? And another thing that would be nice is to actually prove that this Neumann boundary condition is continuous. Okay, so what I decided to tell you a little bit more about today is this recent paper in which what we did is that we did some perturbative calculations that favor these two things that I just mentioned. They favor the fact that the Dirichlet boundary condition disappears and that the Neumann boundary condition is continuous, okay? And I will explain in what sense they favor. Previously, we had studied the same question in pure Yang-Mills theory, okay? So the pattern is very similar, and what perturbative calculation seem to tell you is that indeed that Dirichlet wants to disappear and Neumann wants to keep existing. In addition, there are, compared to Yang-Mills theory, there are some new phenomena when you study the theory with matter. For instance, you can ask yourself, what is the signature in ADS of the existence of a conformal window? I will briefly mention that. And also another very important phenomenon in gauge theories with matter is chiral symmetry breaking. Okay, and I will discuss how you can see that from the point of view of anti-de Sitter. Okay. What does it mean to check perturbatively that some boundary condition wants to disappear? Okay, what does it mean for a boundary condition to disappear? So the mechanism is the same that we mentioned in the previous lecture. So let me go over it again. So the technical name that I didn't mention before is called merger and annihilation, okay? And it was discussed in many papers in the literature. So what is the idea? The idea is that, so we have this family of theories which are parameterized by lambda L, and suppose that at a certain point, an operator O of my boundary theory becomes marginal. So in this case, before it was delta equal 1, and now the boundary is three-dimensional, so marginal means delta equal 3, okay? At some value of the coupling, G critical. Now, if I am at this point, what I said before, right? I add this coupling to the Lagrangian, and this beta function, I can compute it as this form. So you see, what happens is that when I'm before the critical point, I have two real solutions, but when I am above, I lose them, okay? So that's the same idea we illustrated before. And here I just added some more details on how this how do we get these two numbers? Okay, what computation do you need to do? Well, you need to, so those of you who have seen this computation in perturbation theory know already how to compute this. So the way you compute this is that you basically need to do an integral of the 3-point function of this operator. And this is what so what I'm saying is that suppose you compute the 1-point function of O, and you expand both in G, this combination, 1 over G squared critical minus 1 over G, and you expand in Y, okay? So you're gonna have a logarithmic divergence at order Y squared, which is this integral of the 3-point function. But you're also gonna have an additional logarithmic divergence that comes from the bulk, which comes from the fact that the bulk Lagrangian can come very close to your operator and produce also UV divergence. So that's why there are two contributions to the beta function that compete with each other and give rise to this particular form of the beta function that I showed before. Okay? But this is basically inevitable that if before I had whatever is the sign of this A and B, I don't even need to compute this A and B. If a solution existed before G critical, the solution will stop existing after G critical because the sign of this term flips. Okay? That's the idea. Now, so then what we're going to ask ourselves is there any operator that can play this role? Is there any operator in my boundary that can become marginal, okay? And give rise to this phenomenon. And so what are the lead candidates for this operator O that can become marginal in a perturbation theory? So from the gauge fields, I have these two operators that are natural candidates. So if I have the Dirichlet boundary condition, I have this operator JJ, which at weak coupling is dimension 4, okay? With normal boundary condition, I have this operator trace F squared, which also at weak coupling is also dimension 4, okay? And let me consider the case of massless matter. It turns out that also from the matter fields, I get these two candidate operators, which are the lowest singlets. It's not so important the form. What I want to stress is that also them happen to have dimension 4, okay? So I start with all these operators that have dimension 4, and my question is, which one is more in danger to approach 3 and give rise to merger annihilation, okay? So these operators have all dimension 4. So if I want to compute in perturbation theory and see where things move, I need to solve a mixing problem between them. And so the reason that they all have dimension 4 is not just a random coincidence. It's related to what we discussed before, that if you consider a conformal field theory in anti-de Sitter, this is related by Van scaling to boundary conformal field theory. So you see, what I'm telling you is that in the free limit, I have these operators of dimension 4, but in the free limit, I'm just considering the UV CFT, right, of my gauge theory. And the UV CFT of my gauge theory, which is in the limit G equals 0, when I put it in ADS, it becomes a boundary conformal field theory. And in boundary conformal field theory, there is a protected operator, which is called displacement operator, which appears in the bulk to boundary OP of the stress tensor. Okay, so it turns out that what these guys are, so the guys that I'm worried about, the guys that might cause merger annihilation, are precisely the operator that arise when I take, for instance, the stress tensor of Mills and then push it to the boundary. I get this operator of dimension 4. Or I take the stress tensor of my fermions, I push it to the boundary, and I get this operator of dimension 4, okay? So it's not a coincidence to have these singlet operators. They are singlet because they arise from the stress tensor. The stress tensor is always a singlet under all the symmetries. and they have this particular dimension because they are protected by the conformal symmetry of the free theory. Okay, but now I need to ask myself what happens when I turn on the coupling, okay? So for instance, in the case of the fermionic theory, I need to solve this mixing problem. So these are the kind of diagrams I need to compute. I insert my displacement operator, and I need to go on and compute the anomalous dimension. So these are the ones that involve directly this fermionic operator. There are also diagrams that are purely in terms of the Yang-Mills operator, okay? And that we already computed in a previous paper. So of 2024. So now we needed to add also the contribution, the matter. So this is a pretty sophisticated calculation, at least for me. Like, it was a bit long to do, but we managed. I want to say that there is also, precisely using this idea that they are related to the stress tensor, there is another technique to compute these anomalous dimensions using broken conformal word identities. So using the fact that when we move from G0, the stress tensor in the bulk acquires a non-trivial trace, but the conformal word identity is broken in a precise way. And then we can use that to check how the dimension of these operators change, okay? That's another technique that I will, if you want, I can show you later, but I will not describe it. It's more elegant in a sense. But let me just tell you what are the results. So the result is that we compute this mixing matrix of operators, and we get, so we started with two operators, right? There was one from Yang-Mills and one from the matter. So we get two eigenvalues. And so one thing that happens is that actually the eigenvalues that you get with the Dirichlet boundary condition and the one that you get with Neumann boundary condition are precisely opposite to each other. And okay, the precise expression is not so illuminating, it's just some function of the NC and the number of fermions. But the interesting thing is that you see we start with a operator that all have dimension 4, and with the Dirichlet boundary condition, both scaling dimensions go down, okay? While with Neumann boundary conditions, both dimensions go up, okay? So that's the reason why, okay, of course, this is a very weak test because we cannot go all the way to strong coupling, but we believe it's a nice indication that indeed the Dirichlet boundary condition is the one that wants to hit marginality and disappear, while the Neumann boundary condition is the one that wants to extrapolate continuously. It was on loop, yes. I mean, leading order in G. I don't know exactly. Maybe some people would call these two loops, but. So the mixing is the scaling dimensions of these operators. So I have these boundary operators. They all start at G. When I turn off the coupling of Yang-Mills, the gauge coupling, they all have dimension 4. When I turn on the gauge coupling, they start mixing with each other, and I want to know what is the scaling dimension, okay? Because I want to check if they are trying to hit marginality or not. And what this simple computation, I mean, not so simple, but what this computation shows is that when I impose the Dirichlet boundary condition, indeed, this operator seems to want to go down and approach marginality. When if I impose Neumann boundary condition, they go up.
You have those either Dirichlet or Neumann, do those have some mixed boundary conditions or something that what forces you to do that?
Well, the Dirichlet and Neumann are the ones that preserve conformal symmetry and are available, like they are the simplest possible boundary conditions. Now, in principle, you could try to consider more complicated ones. I don't know precisely what you have in mind with mixed. For instance, one thing you can do is you could also consider, maybe that's what you have in mind, like, I don't know, with a theta term, there could be some more sophisticated boundary condition that mixes the modes, but we didn't consider theta term so far.
And so this boundary condition is the gauge field.
For the gauge field, yes. Yeah, yes. For the matter, I just very briefly flashed it, but we are considering the massless case. And I mean, for the fermions, basically there is not so much to discuss. There is something to discuss regarding the dependence on the flavor index. I will discuss it later. But let's say you take this, the simplest possible, and then the boundary condition is like this. It behaves like z to the 3/2. For the scalars, so massless in this case means that I choose the conformal mass. And I chose this boundary. There are two possible basically, and I chose this one.
Eventually, you could mix the one.
Well,
Like you're gonna choose something different for the scalar, something different.
yeah, I mean,
For the HPA,
I have basically for each field I have two possible choices. Yes,
combination.
I can consider combinations. Yes,
That's
yes.
what you show this one.
Yes, it's the thing that we actually did was to, for the gauge fields, chose either Neumann and Dirichlet. For the matter, we fixed this for the fermion and this for the scalar. Yes. Okay. Okay, so now this, of course, it's conjectural. We didn't prove this, but what is compatible with our perturbative computation and we find appealing is what we suspect happens is that this boundary condition, like the Neumann one, continues to flat space, while the Dirichlet one is such that you see there is this operator that gets a more negative anomalous dimension, and at some point it will hit marginality. So this is just, there are two solutions of the beta function, right? Always. So another way to phrase this merger annihilation is that there are two conformal boundary conditions that they meet each other and they become complex. Okay, so this is what we denote by this red. We call it D-star boundary condition. But this D-star boundary condition at the moment, it's a bit mysterious. What is it at weak coupling? Okay, it could very well be that at weak coupling it doesn't exist as a unitary boundary condition, but should somehow emerge here in the vicinity of the disappearance. Okay, so that's what the scenario that we propose. And yes, and then asymptotically these things should shoot like linearly in L, because the coefficient tells you precisely the mass of the particles. Okay? How am I doing with time? Okay. Now, so this, that's all I wanted to say regarding these dimensions, this mixing problem and the relation to merger annihilation. Now, in the remaining time, I want to say a few things regarding conformal window, okay, and how do we see it from the point of view of anti-de Sitter, and then something about Karat symmetry breaking. But let me remind you a very nice story that, so if we consider QCD with like fundamental fermions, let's say we fix the gauge group to be as U and C as we said before, and then we vary the number of fundamental Dirac fermions. Then there are different behaviors depending on the number of Dirac fermions. So of course, if we exaggerate and we put too many Dirac fermions, then we reverse the sign of the beta function, and the theory stops being asymptotically free and becomes free in the IR instead. Okay, this is what happens when NF is larger than 11/3C. And then we're also all familiar with the fact that for very small number of flavors, instead the theory confines, okay? But there is this regime in between, okay, when NF is smaller than 11/2C and larger than some unknown critical value NF star, in which the theory instead is believed to flow to an interacting conformal fit theory in the IR. Okay, so this is called the conformal window of QCD. Okay. Now, if we are in this window of values, what do we expect to see in anti-de Sitter? We expect to see that, you see, instead of the dimension, instead of the boundary condition disappearing or the dimension shooting to some linear trajectory at large L, they should instead flatten out, right? Because what happens is that in the deep IR, we approach this boundary conformal field theory, and the scaling dimension should approach the boundary spectrum of the BCFT that lives in the IR of my RG flow, okay? So we expect a different behavior of this sort. Now, in particular, for one operator, we expect that it should approach, this constant value that it should approach should be 4. What is this 4? I told you before that when I have a BCFT, there is always a protected operator, which is the so-called displacement, okay? And so the fact that we have a conformal symmetry in the IR implies that if I am in the conformal window and I go to large ADS, I should see at least, to the very least, I should see one operator of dimension exactly 4. And then one nice little check that you can do is that using this thing that we computed at one loop, you can check that this prediction is satisfied in the upper end of the conformal window, okay? So it turns out that if you go very close to this 11/2, you can do an expansion 11/2 minus epsilon. You can do an expansion in this epsilon, and this is perturbatively reliable. Strictly speaking, if you want to make this rigorous, you do it in the so-called Veneziano limit, which take large number of flavors, large number of colors with fixed ratio. And then you have a perturbative fixed point for the beta function. So you can really see in this limit the existence of the boundary of the IRCFT, order by order in epsilon. And then you can ask yourself, if I sit now at this fixed point, do I see in anti-de Sitter the displacement operator, okay? And indeed, if you use the scaling dimensions we computed before, you see that this one loop contribution precisely cancels when we plug. So what do we need to do? We need to take the formulas we had before. They were functions of the coupling, right? And we need to plug the value of the coupling at the fixed point. Okay, we plug the value of the coupling at the fixed point, and magically one of the two, just the linear order disappears. Okay, so what this means is that when I am in the conformal window, one of these operators approaches again for at strong coupling. Here I'm seeing just at leading order, a leading non-trivial order in epsilon. So I'm leading non-trivial order in epsilon, I cannot see this little bump. A leading non-trivial order in epsilon, I just see a flat thing because I just see this 4. But I'm just saying that it's very easy to understand that if you will go to order epsilon squared, you will see this little bump and then the operator going again 4. Okay, but it's a nice check that at least one of the two operators doesn't get corrected as we would expect. While the other one just gives us a number, which is the dimension of some operator in the boundary CFT of the conformal window. Now, there is this nice thing that we can observe about the Dirichlet case. So in the Dirichlet case, you see this operator has dimension a little bit below 4, right? Now, you can ask yourself, what happens if I move deeper and deeper inside the conformal window, okay? So this epsilon is going to start increasing. And I'm getting a little bit stressed because this operator has dimension 4 minus something, and epsilon is increasing. So could it be that at some point this guy hits 3? Okay, so let me do something very dirty and extrapolate this one loop answer to estimate when this operator hits 3. Okay, if I do this, I get this number, and we were very surprised to observe that this number that you get is very close to estimates that people have for this end of the conformal window. Okay, so there are various techniques that people use to estimate where the conformal window ends. So it seems to be somehow that there is a relation between when the unprotected operator hits marginality and then on the conformal window. So let me explain. Yeah, so that's what I said. It's close to estimates in the literature. So could it be that we can study the end of the conformal window, can detect it from the point of view of the boundary CFT? And indeed, there is a logic that explains this connection. So the logic that explains this connection is that you might want to require that the data at the boundary of ADS should be continuous in the limit of large radius as a function of x. So x is this number of flavors divided by the number of colors. Okay. So let me explain this point. So we know that as soon as x becomes smaller than the critical number, right? Then it's what we said in the first part of the seminar. When I'm in the confining phase, then we know that the operator should hit marginality and the boundary condition should disappear, right? So if we want continuity across this x star of the spectrum at large lambda L, then this should remain true also if we are just a little bit above x star, okay? So maybe it's better illustrated by these figures. So you see, if I call x bar the point in which my boundary operator hits 3, okay? In the setup in which x bar is larger than x star, then I have everything is continuous, you see? I have this regime in which D exists as a real boundary condition at large lambda L, and then here D instead becomes complex. So this x bar separates the two. I know that the confining phase must have complex D, so everything here is continuous, and this is the point where the operator hits marginality. On the other hand, if I would have the other situation in which x bar is smaller than x star, then this would be weird because you see I would have that until here D exists in the whole conformal window, the Dirichlet boundary condition exists, the Dirichlet boundary condition, and then as soon as I transition, it becomes complex. Okay, so this seems strange, and so by using this continuity argument, at least I get an inequality. Okay, so what we are able to estimate is this x bar, and this inequality at least justifies why there is a connection between the two numbers. How much time do I have? Okay. So is this? Yeah, this was. We were surprised that we have this connection to the end of the conformal window. Okay, I'm almost done. So in the final part, I just want to mention what ADS has to say regarding chiral symmetry breaking. So an interesting observation is that, so as we already mentioned in the second lecture, there is an ADS version of spontaneous symmetry breaking, which is that the symmetry gets broken by the boundary condition. Okay, you have to think about this, like we said before, as the idea that if my the boundary condition is at infinity in space, right? So if the boundary condition breaks a symmetry, it means that the symmetry exists inside my space, but it's broken at infinity. That's exactly the same idea of spontaneous symmetry breaking in flat space. But now you realize that when you study the theory in ADS, even if you're at very weak coupling, it's impossible to have a boundary condition for the fermionic QCD that preserves the full chiral symmetry of QCD. This was observed already a long time ago in this paper by Rattazzi and Reddy. And a modern understanding of this statement is that we know that this symmetry has Toft anomalies, and it's impossible to impose boundary conditions that preserve a full symmetry if the symmetry has Toft anomalies. Okay, so even if you're at very small coupling in anti-de Sitter, you put QCD, immediately you find that it's impossible to preserve this whole symmetry. The symmetry must be broken spontaneously, even at G tiny. And so technically, the way it works is that the general boundary conditions you can impose on your fermions are of this form. So you can stick here some matrix that acts on the flavor indices. That's the general form of the boundary condition. This matrix needs to square to the identity. And okay, you also need to add some boundary action. So this boundary action, you see, it's suggested because it has the form of a mass term. And now, yes, okay, so this of course means that then the boundary operators are going to satisfy the condition that come from the epsilon going to 0 limit of this. But the interesting point of this slide is that I want to tell you that the boundary condition for fermions in ADS contain a new parameter, and this parameter is a flavor matrix. Okay, you cannot avoid that. And once you pick this B, what is happening is that the symmetry SUNF left times SUNF right is broken, spontaneously broken to the subgroup that commutes with this matrix. Okay, so you can do that calculation in free fermionic theory. You don't even have to consider the gauge coupling. You can just compute this condensate in ADS. And this condensate has this beautiful form. So you see it's aligned with this flavor matrix. It's precisely proportional to Bij. And it starts like 1 over L cubed. So that's why we don't see this in flat space, right? In flat space, L is infinity. And then it has an expansion in the gauge coupling, okay, if you want. But you see, in ADS, even at G equals 0, there is symmetry breaking. Now, you also have some analog of the pions, which is precisely also what we saw in the second lecture. So you can take your currents and you can look at the flux at the boundary, and you see that there are these operators which have precisely dimension 3, okay, which is precisely the dimension of scalar operators that are dual to massless scalars, right, in the bulk. So these are the analog Goldstone bosons. So you have these operators at the boundary, which are the analogs of Goldstone bosons. And the terminology that people use is they call these tilt operators. I'm not completely sure why tilt, but that's the name. Now, however, there is a question that arises, which is, you see here, when the coupling is small, when I just have fermions, I can make any choice of this matrix B. And there are many possible patterns of breaking of this SUNF left times SUNF right. Just my choice, what matrix I choose. However, the observation is that, of course, we know that in flat space, one choice is selected, which is the diagonal breaking, right? We must break this to SUNF vector as required by Papa-Witten, or also as we see in nature. And now this gives rise to a little bit of a similar puzzle to the one that we discussed before, because now I can ask myself, suppose I impose Neumann boundary condition for the gauge fields, then there is no discontinuity in my extrapolation from small ADS to large ADS. There is no discontinuity due to the gauge fields, because the theory is confined already at small ADS if I impose Neumann boundary condition, but there is no confinement and confinement discontinuity. However, if I started with a B that is not the one realized in flat space, something must happen to this boundary condition. So in the same sense as before, I claimed to you that I can understand confinement by saying that only the Neumann boundary condition survives in the flat space limit of ADS. I can also formulate a similar question for chiral symmetry breaking. So I would like to see, so I can formulate proving chiral symmetry breaking in flat space. I can formulate it as the problem of understanding that out of all these boundary conditions, only the one with this particular B survives in the flat space limit, okay? And at the moment, this has not been studied, but we just point out that this is something concrete that could be done. So, for instance, one could try to understand what is the sickness of all the other boundary conditions would be different from this. At the moment, it is not known. But there must be some sickness. Okay, so let me conclude with some questions for the future. So I think that I would really like to understand better is how do we go from this formula for the condensate in ADS that we can compute order by order in G to the formula that we all know and love in flat space, in which here instead you have lambda cubed, where lambda is a dynamically generated scale, okay? So here we have this interesting function, which eventually, when G is large, resums in the dynamically generated scale with some coefficient in front. So many interesting questions here are, for instance, how good is this perturbation theory? What is the property of this perturbation theory? How do we see that it resums to that particular non-perturbative factor? That's something that I would like to understand better. So yeah, that's the first thing I said. Can we connect the perturbative ADS condensate to the non-perturbative flat space one? As I mentioned at the end, one thing that I would like to understand is what happens to these wrong fermionic boundary conditions, the one that don't satisfy Vafa-Witten. How do they disappear? More practically speaking, perhaps it would be nice to, there is a lot of work in recent years on S-matrix bootstrap for amplitudes of pions in QCD. And here we could try to formulate it from the point of view of the boundary CFT by doing by studying the correlation functions of these tilt operators that I showed you before, the one that arise from the currents. And one could ask whether the conformal bootstrap can give some results that match the ones of the S-matrix bootstrap. We didn't study yet the consequence of the ABJ anomaly. So, you know, there is the eta prime among the Goldstone bosons that gets a mass from the anomaly. So this means that out of this, all these operators that I mentioned before, these tilt operators, one of them should stop being protected. It should stop being protected because of this anomaly. So this has not been worked out. It would be nice to work it out. And another thing that I'm thinking about now a little bit is if we can apply similar ideas as the ones we saw for the conformal window in 4 dimensions to give some estimates for the, there is an analog question of conformal window in 3-dimensional QCD and also QED. One would like to know what number of flavor separates conformal phase from confining phase. And since it seems like here we have a new tool to estimate this number, I would like to study it and try to apply it there. Okay, thank you.
Thanks, Lorenzo, for a great set of lectures. So this finishes Lorenzo's part of the workshop. Yeah, sorry.
So you showed the lower limit of the conformal window at F star. Is it really hard to find an F star?
Yes, in the sense that it's a strong coupling question, and what is known about it is from lattice simulations, but it's a bit hard because you know, to really know if something is conformal, you need to take your lattice large and see if things you know, decay like powers. So it's a delicate question. So last time I checked, there was still a little bit of a debate in the lattice community regarding whether an F equal 12. Sorry, lattice people also like to concentrate on the case of 3 colors because it's the more relevant for nature, most relevant for nature. And then, but so for 3 colors, there was still a debate a few years ago. Now I'm not super updated regarding the case of 12 flavors, if it is conform or not. So I'm telling you this just to say that it's not an easy question. It's not like you put it on the lattice and you immediately know the answer. Other thing you can do is that you can try to do, people computed the beta function of QCD up to 5 loops at the moment. So you can try to take these 5 loops and try to do some presummations and try to estimate where this beta function stops having a 0. So yeah, those are the things that you can do.
Maybe relate to this question, but I mean, if you go supersymmetric, I guess much more is known about the follow window.
Certainly.
One.
Yeah. In that case, thanks to cyber duality, yes.
So does it make sense to do your calculations with many components?
Yes, I could do that. Unfortunately, there is a little. So yeah, supersymmetry is great because it allows you to have more control on non-perturbative stuff, and you want to have at least 4 supercharges, right? That's at least the lore is that with 4 you can start having some non-perturbative handle. Now, if I introduce the boundary, so I take the theory that I put it in ADS, this typically will break the 4 supercharges to 2. Okay, so I'm gonna have, like on the boundary, I'm gonna have like something like 3D n equal 1 super conformal field theory. And 3D n equal 1, I'm not so sure that I have a lot of handles to actually answer this kind of. So for instance, I could ask, where does the Dirichlet boundary condition for the conformal window of super QCD, for what value of X does it disappear? I'm not sure that 3D n equal 1 is going to be enough to answer this question analytically. One thing you can do is that you can study n equals 2 gauge theory in anti-de Sitter, and then there you really have some non-perturbative handle on the dynamics. Unfortunately, n equals 2 gauge theories, as far as I know, do not confine, so you cannot really ask about confinement, but you can ask about the Coulomb phase, yes, stuff like that.
Any more questions? Okay. Thanks a lot for the answer. We'll be continuing immediately with the final talk before lunch. Okay. Next up, we have Kostas. Victoria will talk about spin chains for general livers.
All right, thanks, Sam, and thanks to the organizers for the opportunity to present here at this beautiful location. Today I would like to discuss some work that we've been doing recently with Jared, who's in the audience. and which will hopefully appear quite soon. And it involves some kind of new types of spin chains that appear in n equals 2 superconformal theory, as I will explain. So that's what I'm going to be discussing. I'll say a few things about, remind you what spin chains, which are one-dimensional quantum mechanical kind of, objects arise in n equals 4 super-EMLs. And then I will break supersymmetry down to n equals 2 and discuss the marginal deformations of these. And I'll do that by orbifolding. And then I'll kind of very quickly, not with too many details, discuss the computation of the planar dilatation operator in these n equals 2 deformed theories. I will characterize the spin chains that one gets in this context, and then I'll summarize. All right, so let's start from n equals 4. If you're not too familiar with n equals 4 SPM-mills, it's okay. I'm not going to really somehow introduce it too much. But it is the maximal supersymmetric theory in d equals 4, where the spectrum of the theory is a gauge field. There are 4 spinors, and what is going to be important for us is that it contains 3 complex scalars, phi I, which are all n by n matrices. So this is a theory that doesn't have any flavors. Everything is just n by n matrices. And we are going to be using the superspace notation for not for any super important reason, but it's just makes things more compact and kind of nicer. So we would write down actions like these, where these are the kinetic terms, these the gauge field, and it couples to the scalar fields, where here this is not the actual scalar field, it's something which is what we call a chiral superfield, which combines the scalars, the fermions, and some auxiliary fields in kind of one object here. And what is going to be most important for us is this interaction term between these chiral superfields, which is called the superpotential, which for n equals 4 takes this very simple form. It's that x commutator y z, it's in the trace because these are matrices, or you can write it in a more symmetric way like this if you define these phis to be x, y, and z. Each of these 3 phis. The theory is invariant under SU4, which rotates these fields among each other and the supercharges among each other. For those who haven't seen superspace, this is not the actual potential. From this, you can derive the potential, which is quartic in the fields, through this formula. All right, so that's kind of all I'm going to say in terms of introduction, but of course you can ask me if you want to know more about n equals 4. But the main starting point for my talk is the work of Minahan and Jarembo some years back, where in the planar limit, of course, okay, this is a gauge theory, maybe I should go back, the observables are gauge invariant operators. In the planar limit, we can focus only on single trace operators, because they don't talk to the double trace and multi-trace operators that much. For instance, you can write down a trace like this, and your goal or your question is how do you find the dimension of such an operator? Which, given that this theory is super conformal, should have a precise answer, because these theories, conformal invariance tells you that you are having the dilatation operator, which is part of the superconformal group, should be an exact symmetry of your theory, and that means that you should be able to every operator kind of diagonalize, or in a set of operators, to find what is known as the anomalous dimension. So this problem is difficult because you have many operators. I mean, depending on the length, meaning how many fields you have in your trace, these mix. And if you take just one, let's say the one I wrote here, this does not have a definite anomalous dimension, or a definite dimension. So you have to find the right linear combination. So it's a kind of big mixing problem, which luckily for the case of n equals 4, is very kind of easy to solve, a bit still technical, but it's possible to solve, because the dilatation operator acts exactly like a Heisenberg XXX model Hamiltonian. So this is a one-dimensional quantum mechanical system for a ferromagnet, and it turns out that on this basis of operators, you just get basically a Heisenberg Hamiltonian. And that is integrable, which means that you can use lots of techniques from integrable systems and the Bithian sets that I'm going to kind of show a little bit later to solve this problem. And that's the one loop. But actually, it turns out that it works also at higher loop orders. At some point, of course, calculating this explicitly becomes difficult. Then you have to rely on symmetries. You have to also use a DSCFT, which n equals 4 is also part of. But using all of these together, it's possible to find the full non-perturbative solution of the spectral problem for a planar n equals 4 superunits. Okay, so this was a very impressive development some years back. And as an example, maybe the most kind of iconic kind of example of this is the calculation of the Konishi operator, which is this short operator, which these are the scalar superfields of n equals 4, which you could solve at basically the full non-perturbative problem. So this is all loops, strong coupling, and as a function of the 't Hooft coupling lambda. And this is the graph that one gets. This is a numerical solution, but of course, a very well-defined set of equations where here you start from perturbation theory. So the first few kind of, this region here you can access with perturbation theory. This region here you can access using the dual string side. And you can see there's some expected value, 1/4 power of lambda, and then some subleading coefficient, so that you can access from the string side. And the numerical solution using integrability kind of precisely interpolates between what you would expect at weak and strong coupling. There are other cases, but this is kind of the first one that was really shown. And okay, I mean, one cannot emphasize enough that this is an amazing result for a 4-dimensional interacting field theory. Okay, it's in the planar limit. Okay, it's supersymmetric, but we saw Joao talked about some similar results yesterday, but of course that was for in the context of matrix models. This is a real interacting 4-dimensional field. So it's something that one can aspire to and try to maybe get something similar for more realistic theories, because of course, okay, that's for n equals 4. Can you get some, maybe fraction of this result for more realistic? So one of the ideas, which I'm going to be following today, is to lower the amount of supersymmetry by the minimum amount possible. So do the minimum possible change to your n equals 4 theory. And the starting point would be to do a Z2 orbifold, and I'll explain what that means. Basically, you take n equals 4, you double the gauge group, and as I said, you have these 3 complex scalars. So you do a projection where V is the gauge field. You don't touch the gauge field, but you take x and y to minus x and minus y. You don't touch the z field. Why not? Because you want z, which is an n equals 1 superfield, to still be in the same multiplet as v, which is the gauge field, to make an n equals 2 theory, because v and z are going to come together into a vector multiplet of n equals 2, while x and y are going to become what we call a hypermultiplet of n equals 2 supersymmetric gauge theory. And but at the same time, okay, if you just do this, you don't going to get much. At the same time, you need to project in color space, meaning these are 2n by 2n matrices. This is a block 2n by 2n matrix. So you do this projection here, and you end up with breaking your gauge group to SUN times SUN. So you have 2 gauge groups now. And you have projected also your gauge fields, so your matter fields in this particular way. So Z is an adjoint in each individual gauge groups. These are blocks of n by n. So it goes together with the vector, which is also blocks of n by n. But these ones are bifundamental, meaning that they talk to both gauge groups. So one index is of the first gauge group, the other index is of the second gauge groups. All right, so the way to present this kind of nicely is using something known as a quiver diagram, where each node is one gauge group, and you can put an arrow telling you, okay, this x12 is the bifundamental that takes you from 1 to 2. So it's a charge under both of these gauge groups. Z are the adjoints, so they go back to the same gauge group. This potential gets expanded in a particular way. SU4 is broken, of course, and why is it broken? Because, well, let's see, there used to be a symmetry or a raising operator that could take your z to an x, right? So the z and x were the same thing. They're both adjoints in the n equals 4 context. So you could raise the z to an x. but now your Z is an adjoint, your X is a fundamental. So obviously this, doing something like this does not respect the gauge structure anymore. So you've lost these generators. So you've lost basically half your R symmetry generators. However, by doing this, the integrability structure was shown or known for quite some time that is not affected. So if you just reduce the supersymmetry, you still have the same number, the same amount of integrability or the same power of integrability. So we're going to do something slightly more interesting. We're going to move away from the orbifold point. So remembering that there are, in this case, two gauge groups, SUN1 and SUN2. These have the same gauge coupling at the orbifold point because it just descends from n equals 4. Here we're going to vary those couplings independently. Okay, that's the main new thing, let's say, compared to the old results of Weisert and Reumann and so on. So we're going to have now two terms in the superpotential which now have a different gauge coupling. This deformation is known to be marginal, meaning that it preserves n equals 2, not only n equals 2 supersymmetry, but also superconformal invariance. So you can do this without really affecting your, the definiteness of your theory and all of these things. But it was studied some time ago by Rastelian collaborators, Eli Pomoni and Abhijit Gade. And the claim that was made there is that once you do this, when you move away from the orbifold point, integrability is gone. So everything else is fine, but integrability seems to be lost. So they studied the Yang-Baxter equation, scattering of magnons on the corresponding chains, and they found that things don't work out anymore. But still, I think the perspective we are taking right now is that integrability is nice to have, but of course we know real life is not integrable. Can we still, even if it's not technically integrable by the standard tests, are these theories interesting to look at and study the spin chains that one gets in these kinds of theories? And we'll worry about integrability or similar structures later. So we did that with Eli and a student, Randall, some of you might know him, some years back, where we studied the two magnum problem in these two theories. So we solved the two magnum problem for some specific sectors. This was extended recently by Eli's group at DESI to 3 magnons and 4 magnons. And okay, so technically, at some point when you are starting to solve like 3 magnum problems, that already indicates some kind of integrability because you can solve. So 3 magnum scattering is where integrability really starts playing a role. But the situation here is a little bit more muddled because to be able to solve these problems for 3 and 4 magnons, they had to introduce an infinite number of long range kind of interaction terms in their what we call the Bethe-ansatz. And so but of course there was some structure, but it was not like a very, very simple result like in n equals 4 or the Heisenberg chain, where you just have some plane waves and they scatter and there's an S matrix. Things looked a little bit more complicated. So I think the jury is still out about whether this is an indication of integrability. But what it is definitely an indication of is that there is more symmetry in these theories that is naively visible. And one of the things that we did last year with Eli's group is that we showed that these SU4 generators that a couple of slides ago I told you they were broken because you cannot take up a fundamental to an adjoint. Actually, they can be revived. So there is a way of making this possible to take things that are charged under different gauge groups to map to each other. If you move away a little bit from this notion of a Lie algebraic SU4 group, this is the flavor group, but make it into kind of something which we call a twisted groupoid. I'm not going to go into that. I've given talks about that in the past, and you can ask me if you want to know about it, but this is not what today's talk is about. But we are working on making this notion of what is a twisted groupoid more rigorous. There's a related concept of what is called a dynamical dilute temporally Lieb algebra that is quite interesting. There's quite a lot of work also by Giovanni Felder on some related concepts called restricted quantum groups. So we're talking with Giovanni and we are trying to see if we can make something more formal and rigorous about this, which might be in a sense predictive and allow us to kind of fix some ambiguities in our constructions and all that. So we're not there yet, and I'm not really going to talk about that. But it is interesting. However, Z2 is also not the most generic thing you can do. It's actually the least generic thing that you can do when you want to talk about n equals 2 theories. And one of the reasons is that if we go back a little bit to the quiver diagram, you see that, or to this picture here, you see that there is asymmetry here. So there's an x which goes from 1 to 2, but there's also a y that goes from 1 to 2. So there is an SU2 symmetry which kind of relates these. There's the symmetry symmetric under this. And you can see it here as well when I said it's broken. This is the usual R symmetry of n equals 2 theories, but there's also an extra SU2 symmetry which should not really be there for a generic n equals 2 theory. So Z2 is still a bit special. So what I'm going to be discussing today is thinking of more general orbifolds that lead to n equals 2 gauge theories, actually the most general case, and studying the spin chains that come out of those, which have not really been looked at before. So what we're going to do is orbifold n equals 4 by any discrete subgroup of SU2. Why SU2? Because SU2 is the symmetry in the upstairs picture. Like, if you're thinking of the X, Ys, and Zs, remember X and Y became minus X minus Y, but that was just Z2. You can now take X and Y and orbifold them by any representation, but you won't keep Z the same, hence SU2. Otherwise, if you did an SU3, you would have an n equals 1. You'd reduce your symmetry even more. That's for the future. It can be done, but we're not there yet. So we're looking at discrete subgroups only of an SU2, and these are, of course, classified. They're the cyclic, binary, dihedral, tetrahedral, octahedral, and icosahedral, all binary, which are related by the Mackay correspondence to the simply laced linking diagrams, so the AD groups, hence the name AD spin chains that I've been using. So to impose invariance under this, well, you choose your group. So it's one of these groups. You choose under any possible element of those groups. Then this is how you impose it. So you do a conjugation with this element gamma as represented on your space of your gauge indices. So this you have to have a big enough gauge group, SU not 2n now, but SU some number times n, so that you can do this projection consistently. And at the same time, you also have to do a rotation in R symmetry space. This is the SU2. But okay, this is kind of relatively simple to figure out. And this, of course, has been done at the orbifold point. And already Bison and Royman looked at some of these cases, but there was also another later paper by Solovyov, where integrability was shown to still be there, even for these more general orbifolds, so beyond Z2. But of course, when the gauge couplings are equal, integrability there is not very different from the n equals 4 case. So despite this kind of projection that you're doing. So what we're going to be doing now is, of course, looking at the case where we marginally deform. So you think of all these couplings as independently tunable. So you have quite a large number of couplings. And these are the kind of diagrams we're going to be getting. These, of course, are the Dicke diagrams of the ADE groups. But for us, they are the quiver diagrams. So these are the analogous diagrams of that quiver that we wrote, where you have now a certain number of gauge groups. The gauge groups is what here is written as M. So this is the number of nodes that you have in your in each case. And there are two infinite series, the A and the D series. A1 is Z2. And so when you do the orbifold by Z2, and you can see why it's special. I mean, there are two lines between the same two nodes, between two different nodes. All the other ones do not have this feature. So they're much more generic in that sense. So this is the reason for this extra symmetry for the Z2 case. So here, H counts the number of hypermultiplets. So hypermultiplets are how many fields go between any two nodes, as in both 1x and 1y together, they make hypermultiplet. So you have all these cases, and maybe just for notation, just to write out the Lagrangian in the next step. So you have multiple gauge groups, because as you can see here, for some of these, the gauge group is not n, but it's actually 2n or even 3n or even 6n. So the gauge groups are also not the same. They're not all SUN gauge groups, unlike the circular quiver. Some of them are multiples of that. So to take that into account, we introduce a small n parameter here. So it's a product of different gauge groups. For the bifundamentals, often I'm going to be using Q
For the adjoints, we're going to be using often phi, just an alternative notation that is often convenient. And those quiver diagrams of the previous slide can be represented as adjacency matrices, meaning that, well, there's a connection between node 1 to itself. That's a Z field, because it will go from the node back to itself. But node 1 can be connected to node 2, but not to node 3. And that's why there's a 0 here. So you can represent that quiver, let's say, of ZK in the previous slide as, so this one, in terms of that particular adjacency matrix. For D4, that was another example, then D4 means that this one is connected straight to these two. So that's another adjacency diagram, which is this one, and so on. So you can write down these adjacency matrices. You can reduce them to only focus on the hypermultiplets, meaning that you basically take away the trace part here, and so you have zeros on the diagonal. That's what we write here. And you can combine them with these ends, just this is an annotational convenience, to write some coefficients like this, where you also multiply by the size of each gauge node. Okay? That's the gauge group, how many times n that is that gauge. So with that, you can write down the superspace Lagrangian, and here I've indicated the differences from n equals 4. So the difference from n equals 4 is that, let's say for these are the again, if you don't know superspace, it's not so important for now. But there are some, these are kappas are the marginal deformations. These are the couplings that are different. These ends are these, rank of the gauge group coefficients. And there are some, these A's are the adjacency matrices for the hypermultiplets. And maybe the most crucial element is the superpotential, where these D's that are defined, which are these kind of rescaled adjacency matrices, they affect the superpotential. So the superpotential, you can, if kappas are 1, you're at the orbital point. That's where it's integrable. If the kappas are, but it's still different from n equals 4, of course, because you have this adjacency structure. But if you move away from the orbital point, you get these kappas. All right, so now what you want to do using this Lagrangian, okay, I'm skipping steps, of course, there are also ghosts you have to take into account. I mean, I just wrote the more important part of the Lagrangian. What you want to do is calculate any two-point function of any gauge invariant scalar operator. So we're focusing on the scalar sector. So these are operators like this. You can have Qs, which are the bifundamentals. You can have Phi, you can have their conjugates. The crucial thing about this is, of course, that, and that's why we're interested in this, at least from a mathematical perspective, is that your Hilbert space becomes restricted. That means that, when you are putting together these operators, you have to follow the arrows. So if there's a quiver and has an arrow going from 1 to 2, you have to kind of, if your field that you put goes from 1 to 2, the next field has to be starting at 2 and going somewhere else. And so that's called a path algebra. And there's a kind of nice mathematical kind of way of understanding it, which led eventually to this groupoid story that I kind of mentioned briefly. That's kind of a modern topic in a sense, also for, again, many mathematical studies of these restricted kind of where not everything can be composed. You can, so groupoids are kind of part of this somehow discussion, and I can talk about. So, okay, what we want to do is calculate all the two-point correlators, as I said, because this is a conformal theory, so your two-point correlators are going to look kind of like this. But of course, this assumes that your O's have a definite dimension, and that's not obvious. This does not have a definite dimension. You have to diagonalize. So but to do it, you need something similar to what Minechan and Zarembo found, like the Hamiltonian, of some integrable system, which allows you to do this diagonalization. So what, of course, saves the day, like in their cases, we're in a planar limit, and okay, at the moment we're only going to be working at one loop, and that means that all your interactions of your one loop diagrams are nearest neighbors. Only fields which are next to each other on the trace. So let's say this one and that one, or this one and that one, can talk to each other in a one loop diagram. So you can kind of organize the discussion easily in terms of a Hamiltonian that you're going to act on on the spin chain. So we're going to be using superspace because, okay, it's fun. It makes things also much more compact, and it's also For n equals for one loop, superspace is a slight kind of overkill. But if you want to go to higher loops eventually, then it's probably essential. So in these theories, so we're going to be using superspace, and I just write it down just to indicate what is happening here. We're working on some generic n equals 2 theory of the type I discussed, and let's say somewhat fundamental. And here, these colors tell you how much time? Okay, so these tell you how much, what node your gate indices live on. For n equals 4, there's only one node, so I'll draw everything as purple. But for these theories, there's many possibilities for the indices, and they affect these coefficients that come out in front. And of course, the marginal deformations are not there for n equals 4 because there's only one node, so there's no different couplings that you can have. So that's not the only diagram. There's a bunch of diagrams that you have to calculate. These are gauge fields that are propagating here. If it's the same indices, that's the adjoint fields. If it's the same node, the same colors. If it's the colors are different, that means I have a fundamental field because they have different, they belong to different nodes. So you have to, take all of these into account, and all of these can be written in terms of the corresponding n equals 4 diagram, but now with additional coefficients. I'm not going to show you the calculation of these one-loop diagrams. Now, of course, if you're not familiar with this, these do not look like one-loop diagrams, but they are one-loop diagrams because you are relating these. This is the one-loop correction to the diagrams where all the fields are like tree-level kind of weak contracted to each other. So this is the first correction. That's a one-loop diagram, even though they look kind of more like two-loop. But in terms of the index structure, you have to keep all of this to be able to understand the correct powers of each diagram. It's also important to note that even though we're in the planar limit, we are still in SUN. All the gauge groups are SUN, so there are some. The propagator of SUN, of course, has a subleading correction, and there's one case where this also contributes at length 2. So here the trace is not open. This is just a length 2 operator. And you can see that, what this does is kind of, the index structure looks like this. And this has the same power, even though there's a 1/n, this has the same power as the leading diagram. So you need to take into account, and it's important to get the right counting of operators. All right, so this is just a very small part of the Hamiltonian. I don't have time to really go through all the details, but, you can write it out explicitly for the generic case. And what I'm going to do now very quickly is to characterize or start characterizing what spin chains you get by acting with this Hamiltonian. So even though some of us work on very maybe mathematical and more formal things, and there's a lot of categorical structure behind all of this stuff, but sometimes as a physicist it's nice to get a new quantum mechanical system and just take it apart and see, or smash things together and see what comes out. And that's what we're going to be doing here. So we're going to be doing some studies, both the spectrum. So and then also we're going to look at some more integrable related questions like Bethe answers and so on. So let's say for Z3, one of the simplest non-trivial cases, that's the quiver. So there are 3 hypermultiplets. There's one untwisted sector, which should have the same dimensions as n equals 4. There's a theorem about that, but there's 2 twisted sectors which can do whatever they want. And then you can start plotting what happens as you move away from the orbital point. So here K0 is the orbital point, so that's here. So that's what energies you get at the orbital point. This is for length 2. So operators with x's and y's, or x's and x bars and so on. And you get something like this. And what is nice to see, this kappa 1 goes to S1 minus 2k. What happens here at this point where k becomes half is that that gauge group, as you can see, the coupling of the gauge group goes to 0, which means that it becomes global. So this is, if you were doing this for Z2, this would exactly be what we call superconformal QCD in the Veneziano limit that was just mentioned earlier. So it's basically what your gauge group is just now a global flavor group. But here you can do this in multiple ways. So this is just an example, but our techniques stop applying to this point because when you are working now with a flavor group, you are basically your spin chain breaks up at that point because some of your gauge indices now become global. So we cannot really go further than this with our techniques, but it's interesting to study this also from this perspective. There are some approaches to study the spectrum of these kinds of theory. Sorry, wrong. All right, so this is for length 3. You see, you get something more interesting, more complicated. Now, of course, when you have a diagram like this, your intuition is to start looking for things like avoided crossings, Wigner von Neumann kind of stuff, and seeing, what you learn about integrability or non-integrability of the system. So far, things are a bit too simple because even though this diagram looks a little bit more complicated, one should note that these colors indicate different twisted sectors. So these are protected by symmetry, they cannot mix with each other. So we're not really learning anything about avoided crossings from something like this. We need to look at more complicated diagrams. Anyway, so maybe one kind of point, which was also made, actually similar to some plots that Lorenzo just showed, is that one of the interesting things about these spin chains is that at length 4 and higher, there are some states which have energy 0 at the orbital point. And naively, if something has energy 0, that means anomalous dimension of 0. Naively, you think of this as a protected state, but many of them are actually not protected. And as you deform away, let's say in this case, I'm deforming kappa 2 to be 1 minus k, you find that it goes to the super QCD limit, but it becomes negative. So some dimensions can actually become negative without violating a unitary bounds, because these are, we look carefully at the bounds and there doesn't seem to be any problem with unitarity. So again, these energies, what this precise one loop energy is in the superconformal QCD limit, it would be very interesting to study directly there and confirm. Okay, I think I'm probably running out of time, so let me kind of, okay, maybe one last thing is, of course, now you can do scattering as well. And scattering in these changes is kind of fun to look at. So, think of these fields, an X and a Y. Blue means Zs. These are the adjoint fields. Red means Zs, but of a different vacuum, because now you can have adjoints of Z1, of Z2. So when an X and a Y come together, they can either reflect. I don't write the reflection here, but they can also transmit through each other. This is just standard quantum mechanical scattering. But now when they go through each other, you see that a new vacuum is produced in between, because there is no, in the Z3 theory, there is no Y12 field. So what is being produced is a Y13 field and an X31 field. And now they drag with them Z3s, which are a new vacuum. The dispersion relation in this new vacuum is different from the old one, which means that their momenta are not the same. They have to have the same energy, but the momenta can differ. The sum of the momentum is the same, but so you get a funny kind of picture here where now these ones can come together again on the opposite side of the spin chain. So now you're thinking of the back of the spin chain. And when they scatter through each other, then they produce the red vacuum. And you can keep doing this, and then they come back with the red vacuum, drag behind them, and then there's a green vacuum, but when they scatter, they produce a blue vacuum. And then when they go to the other side, then you get exactly the same configuration that we started with, which is this, because everything is under the trace. So you can think of this cyclically. So it's a kind of a fun way of seeing, how these things scatter. And now that inspires you to write a Bethe ansatz. I'm out of time, so I'm not going to really go through this, but you can write down a Bethe ansatz for this. You can find the corresponding S matrices that they don't look amazing, but they're not too bad. And you can use those to actually solve for imposing cyclicity correctly. You can solve and find this is the orbital point where the couplers are equal. This is a just randomly chosen point. And you can find all the energies as a function of the momentum of your magnons that are scattering. And okay, you can do the same for D4. I'll go very quickly through it, but you can now in D4 you have 5 couplings, and you can play with them independently, and you can get kind of complicated diagrams. Again, from every point where you see many fields, many different energies emanating, that's a twisted sector, because there's multiple twisted sectors here. So these are degenerate at the orbital point. But as you move away, they become non-degenerate, so that's why you get these things. But they're different twisted sectors, so they don't talk to each other. You can get more complicated things if you deform the couplings differently. Okay, I'm not going to discuss the scattering, even though that's quite fun as well. You can ask me about it, but you can write down the Bethe ansatz, and it also works. We also looked at the E6 theory. That's even more fun, especially from a Bethe ansatz perspective, because now you have 7 nodes, and it's kind of quite complicated to see how all of them have to fit together, and periodicity has to be imposed for all of this to work out. But it's also sort of nice. I'm not going to show you much about it. We looked at the protected spectrum just to be able to check for some sectors like X's and Y's, then the Smolean series should give us the correct numbers, the precise counting of states. And we are getting all of these states. The reason I'm stopping earlier, let's say for E6, is that even this, this takes about 2 days on a laptop to get this number 2, because you have several thousand states for E6 at length. This would be length 12. These would be length 12 states. So it gets a bit more difficult to precisely check them explicitly. But these are the numbers of BPS states that you would get from the index, and you can check that it all agrees. All right, so to summarize, we constructed the one-loop Hamiltonian for the generic n equals 2 theories, which have a Lagrangian description, because there's the theorem is that all the theories that are perturbatively finite can be gotten from this. Of course, there are other theories of class SK and all that you cannot get in this construction. And we studied the spectrum in 3 ways, just by explicitly diagonalizing, by the Bethe and also using indices. And there's many things that we still don't understand about these spin chains. I mentioned some of them, the restricted Hilbert space story, mathematically how to make it precise, weird mixings that don't happen at the orbifold point, and these negative anomalous dimensions is something new. Negative anomalous dimensions in n equals 4 are typically seen only when you go non-planar. But here we are in the strict planar limit. So this is something kind of new and still needs to be understood a little bit better. Integrability was not addressed so far, but of course we just set up the framework, and then we can study integrability a bit more precisely. There are many other descriptions. Of course, I could have mentioned here going to n equals 1 and other things. But also on the gravity side, there's not very much known about these theories. So of course, at the orbifold point, you just take S5 and you orbifold S5 and you have some geometry. But the moment you start deforming away, what is even the precise supergravity solution that you need? Definitely there's going to be B fields and other supergravity fields there. That is not known to my knowledge. So it would be interesting to understand that side a bit better, to be able to start doing some ADS-CFT as well on top of the one loop calculation. Okay, that's all I had to say. Thanks a lot.
Know some curves. There's big sections of those curves. What do you previous?
So you mean when I did plots? Yes.
Yeah.
So this is the orbifold point. So here is where the spectrum is degenerate. So you have, let's say in this case, there are 3 states which have the same energy at the orbifold point. And so then you start moving away from the orbifold point. So you take your couplings to be not equal anymore using this formula. So when k is 0, everything is 1. That's the orbifold point, and now you start making them different. So you see that all the degeneracies get lifted. When you go to the super QCD limit, then you get some more. So this state is going to become probably 0. So it's going to become a BPS state. This state probably is going to have the same energy as that. So some of them do meet, and we get the degeneracies again at the QCD limit. But in between all, the degeneracies seem to be broken generically. But they're not really crossings in the sense of these. What we would like to be able to study is when, let's say, these two, which come from different energies at the orbifold point, they might want to cross, but we're not seeing that. No. This starts from. They might eventually go down, but in this sector, this is holomorphic. In the holomorphic sector, there's no way to get negative anomalous dimension. So these are. This is the anomalous dimension. So what I'm plotting is not the full dimension. This is the anomalous dimension. This is the energy of the Hamiltonian. So these are states which are length 3. So your dimension is going to be 3 plus this value. But all of these are positive value. This value times the 't Hooft coupling square or 't Hooft coupling. But these are all positive. But only for the sector where you have length 4 and you are neutral. is it possible to get this negative eigenvalue issue that's okay, it's a bit far behind. But what I plotted here was length 4, but neutral, not holomorphic. So for holomorphic, I think the unitarity condition is such that you can, like, delta is R somehow, and for short state, there's no way to go below that. But for neutral sectors, they're not protected in the same way. So I guess we have this debate. I think one's not called them BPS. They're just energy or states with 0 anomalous dimension at one loop. It could be that even at 2 loops at orbital points, although I don't think so, because at n equals 4 they don't. But in principle, nothing protects it. So I guess the question really is, why are these states, why do they have 0 energy for n equals 4 or for the orbital point? But in general, it doesn't seem that anything protects them from becoming negative.
And you mentioned that you guys don't see these crossings happen.
But okay, we looked only so far at very simple sectors, right? So this was length 3, let's say, and there doesn't seem to be anything.
Why?
They avoid the crossings. So there are various criteria for when some quantum mechanical system is integrable or not. And usual integrability allows for crossings between, because there's a lot of symmetry. So the more symmetries you have, the more your states are protected from mixing, from talking to each other. So if 2 states start coming close in energy, they can cross through each other because there's no way that they can mix, because there's all this infinite number of symmetry that integrability has. If you have a non-integrable theory, then there's a problem, because your theories might want to, your states, which tend to get the same eigenvalue, might want to mix. And there's nothing stopping them. But what actually happens is that they avoid the crossing. And I think it's a theorem, but for Neumann and Wigner about this. And people who do random matrix probably are quite familiar with these things, that actually what usually happens in non-integrable systems is that they go close, they start trying to cross, but then they move away from each other, because somehow the system doesn't want them to get the same energy and mix. So these are the things that one can study here, but of course we will need a bit more complicated sectors and length 3, which is a few numbers.
Okay. Any final questions? Okay, then I think it's time for lunch. I think lunch is served outside. Let's thank Gustas once again. Oh, you come back up. You're about to speak.
I would be more happy if somehow that
Like it's just put it in some places that are there. It's just generally.
Anyway, I have to go.
That's not enough opinion as how people forward. So somebody gives.
After all, that's very
India.
Thanks a lot. So first I would like to thank the organizers for inviting me.
Sitting,
It's a great pleasure to visit South Africa and to give these lectures. So the title of my lectures is Holography, Bootstrap, and Defects. So I'm going to start the lectures by explaining how motivating two of the three keywords in the title. Doesn't seem to write very well. We get another plus. Maybe I can, yeah. This one's gone. Oh, the blue one. Okay, so let me start with the motivations. Okay. So let's start with why are we interested in holography, or more precisely, why holographic correlators. So by holographic correlators, I mean the CFT correlators in a holographic CFT. So there are many reasons. One of the reasons is that we want to understand analytically the physics at strong coupling. So this is possible thanks to ADS-CFT, which allows us to map a strongly coupled conformal field theory to a weakly coupled gravitational theory in a curved spacetime. So we can, in principle, just do a division theory to analytically understand the physics at strong coupling, at least for a certain class of theories. Another motivation has to do with what people have discovered in flat space about scattering amplitudes. And here we are looking at these objects in a curved background. So let me first explain what is the connection with amplitudes in curved space. So it's sufficient to look at this cartoon where the cylinder corresponds to the ADS space. So at the boundary, this is where your CFT lives. And in the bulk of the cylinder, this is the ADS space where you have the gravitational theory. So these holographic correlators, they are correlation functions operators which you insert at the boundary of the cylinder. And from the bulk perspective, they will excite some wave packets which travel to the bulk of ADS. So they will meet each other and they scatter, and then you measure them again at the boundary. So this is the duality between correlation functions in the CFT and scattering amplitudes in the curved ADS. So coming back to this motivation, so people have described the many remarkable properties of amplitudes in flat space. For example, the so-called double copy relation, which tells us that Yang-Mills squared is gravity. So basically, you can do some manipulation to the gauge theory amplitude, and you can get the gravity amplitude. This tells you there's some very deep relation between gauge theory and gravity. Now, one question you can ask is how robust are these lessons which you have learned in class space? And this ADS setup is a very very nice arena where you can try to explore these ideas. Also, I should mention that these holographic collators, they also show up in what Lorenzo discussed, where he was interested in studying QFT in ADS. So many of the techniques developed in this context will also be useful in what he talked about. So this explains the holography part of my title. Now, second question is why? What has this to do with Bootstrap? So here I also want to clarify what I mean by Bootstrap. So this has to do with some of the difficulties associated with studying these objects. So these hologram collators, they actually much more non-trivial to compute compared to flat space for a number of reasons. First of all, we are now in a curved background. So even doing things perturbatively, this is much more complicated than in flat space time. And also, when we study these sort of top-down models from string theory and M theory, you are usually encountering a situation that you have a compact internal space. And then when you do a Kiki reduction with respect to that internal manifold, this will give you infinite many particles. So this is richer than what we usually have in flat space, because usually in flat space, when you look at scattering amplitudes, you only talk about finite many species of particles, but here, genetically, you would have infinitely many of these particles interacting with each other. And consequently, as you can imagine, the interactions among these infinite many particles are extremely complicated. So this makes the study of these holographic collators very difficult. And this is also part of the reason why for the first 2 decades, like after ADS-50 was discovered, in the literature, there were only finite many examples of these holographic collators, which were explicitly computed. Okay, now what has this to do with Bootstrap? So let me give a very brief review about the history of Bootstrap. So the idea of Bootstrap first showed up in the physics context in the 60s, when people were studying hadron physics. So people were discovering lots of new particles, new hadron particles, and they were a bit puzzled about what is the underlying physics. And one of the radical proposals at that time was proposed by Geoffrey Chu. So basically, he claims that all the hadron particles are equally fundamental, and their physics are basically determined by the interactions being consistent. So this is his hadron matrix Bootstrap program. Where his idea was essentially to impose some very general constraints from symmetries and consistency conditions, including Poincare symmetry, unitarity, analyticity, causality. And his vision was that using just these constraints, it is possible to bootstrap the S matrix, S matrix, which contains all the physics. So this program was successful to some extent. For example, it managed to give you the correct the mass of the row meson. However, largely it didn't deliver what it was promised to do. But then the idea was.
Sorry, one question.
Yes.
You say row meson.
Yes.
Why row meson? I mean, I would imagine pi meson because these are the lightest mesons.
Yeah, you didn't quite do that. I think it was instead of the row meson. Yeah. I think it was one of the simplest things that you can look at. Yeah. Yes. Then, so this idea didn't quite work, but then the idea was borrowed into the study of CFTs. So CFT bootstrap, which was proposed in the 70s by two groups, one in Italy, another one in Soviet Union. And this idea sort of reached its climax in the 80s when it's applied to in the study of 2D CFTs. This is a work of VPZ, so Bielamin, Polakov, and Zamlochkov. So where they find a concrete realization of this idea, where we solve infinite many strongly coupled 2D CFTs by basically just imposing symmetries and condensity conditions. But this was again somewhat special because they had to use this enhancement of symmetry where, in 2D, where conformal symmetry is enhanced to infinite Virasoro symmetry. And it was not clear how it is possible to go to higher D. And for higher D, the breakthrough came much later. Which I think is 2008. So there people managed to find a numerical way to solve the consistency of the constraints of CFTs. And now it's a very powerful method. For example, you can get very accurate estimates of the 3D Ising critical exponents. In our lectures, I'm going to, so what I meant by bootstrap doesn't correspond to any of these, but I'm here just using the word bootstrap in a more general sense. Or in other words, I'm basically just using the general philosophy of bootstrap. What I want to do here is trying to compute physical observables in this context. I meant these holographic collators directly using symmetries and consistency conditions. So I will give you some detailed examples where you can see how this bootstrap strategy works. Actually, it is quite similar to the original proposal of Geoffrey Chu. So let me also mention that in these lectures, I'm going to mostly focused on four-dimensional matrix for imperial mills, which is sort of the hydrogen atom of high energy physics. Although many of the things I explain here apply equally well to other models in string theory. So let me also give some reference. So if you want to have a pedagogical review on these things I will talk about in these lectures, you can have a look at our review written together with Anya de BC and Anning Singha. From 2002. And the schematic plan for these lectures is as follows. In the first lecture, I'm going to review some of the main ideas and tricks of ADS perturbation theory. So in the past, people used these techniques to compute these holographic correlators in the sort of hardcore way. And you will see eventually we won't need any of these, but actually some of these tricks are actually quite useful for other purposes. For example, one is this what I mentioned for studying QFTs in ADS. Another place where it's useful is in the so-called analytic functional approach to conformal bootstrap. So in the second lecture, I'm going to tell you how bootstrap works for the anchors for superior mills. So we will see how we can get all these correlators without going through all these perturbation theory calculation. And I should mention these two lectures, they are about results at least 10 years old. And in the third lecture, we'll be a bit more up to date. And that is where the last keyword in the title comes in. So I'm going to talk about defect CFT correlators. Yes, defect CFTs. And as an application, I will talk about these so-called giant graviton operators and how we can compute their holographic correlators. Okay. So let me So let me start with the first part of this outline. By ADS perturbation theory, essentially what I meant is how to compute diagrams in anti-de Sitter space. So in flat space, these diagrams are called Feynman diagrams, but in ADS, they're called Witten diagrams. So again, you can use this example of Fermi equals forces mills as an example. Now, according to ADS-CFT, this is due to 2B string theory. In ADS5 times S5. What we are focusing on more precisely is this double scaling limit this de Hooft limit, where you first send n, which is the gauge group of the rank of the gauge group, to infinity, keeping lambda fixed, but then you also send lambda to infinity. So when lambda is small, the left-hand side you can directly just compute using standard Feynman diagrams in principle. But when coupling is strong, there's not much you can do. However, the dual description give you a simple way to look at the theory. And in this limit, the right-hand side of the string theory essentially just becomes tree-level supergravity. So basically, large n tells you that you don't need to consider loop corrections. And lambda goes to infinity, tells you that all the stringy states, they become massive, so they decouple, and you only have the massless degrees of freedom, which is the 2B supergravity. Okay, so multiplied by this, so the diagrams we want to look at are these tree-level Newton diagrams. We can also look at higher point correlation functions, but in these lectures, I'm mostly going to focus on the simplest correlation functions, which are 4-point functions. So we know that in a CFT, 2-point function and 3-point functions are determined by symmetry. The first non-trivial correlator is at 4 points. So okay, so what kind of diagrams can we draw at for 4 points at tree level? So there are only 2 types. One is called the contact Witten diagram, and the other one is called exchange Witten diagram. So this looks very much similar to what we have if we draw a bubble around it. So what this diagram means is that so this bubble represents the boundary of ADS. That's where you insert your operators, and the rest of the diagram is has the exact same meaning as in flat space. So to build these diagrams, what you need are propagators, right? So you have here 2 types of propagators. One is called the bulk to boundary, because it has 1 point on the boundary, the other one in the bulk. And the other type is bulk to bulk, because both points are in the bulk. So the prescription is actually similar to flat space. You basically write down the integral for this diagram using vertices and the propagators, and then you integrate the points where you invert the vertices. So now I'm going to explain to you how schematically we can compute these diagrams. So these diagrams are the building blocks of ADS perturbation theory. So let's first focus on contact Witten diagram. So in the literature, these contact Witten diagrams are also called D functions, denoted by the letter D with some lower indices, which are the conformal dimensions of the operators you insert. So what are these? So as I said, you basically just write down this diagram according to this graph. So you have a product of all the propagators, bulk to boundary propagators. So here I'm doing this more generally. I'm looking at the endpoint function. So you have a product of these propagators, which take a quite simple form. So here I'm using the Poincare coordinates. So my metric is as follows. So Z0 is the radial direction, and the directions parallel to the boundary, I denote them with a vector arrow. So these operators, they're inverted at xi locations. So this is the back-to boundary propagator. Now, after you multiply them together, you need to integrate over the common bulk point z. So you also have this integration measure. Okay, so if you compute this integral, this is the value you get for this diagram. So how do we compute such an integral? So there are some standard tricks which were used in the literature.
The vector z should have a subscript, right? Z.
Sorry. Yeah. Thanks for pointing that out. So there are some standard tricks. The first trick we need to use is so-called Schwinger parameterization. So I'm just going to outline the main idea. The technical details you can read in this review. I just erased. The Schwinger parameterization, let me remind you what it looks like. So basically, if you have something that looks like 1 divided by a to the delta's power, you can write this as an integral over some variable, let's call t, from 0 to infinity. So you have integral of dt, t to the delta minus 1, e to the minus t times a. This is the elementary identity, which you can check for yourself. The nice thing about it is it moves this a from the denominator into the exponent of the exponential. And here we are going to do it for all these denominators in this propagator. The point of doing that is after you do the Schwinger parameterizations for all these endpoints, the z integral, the z vector integral, becomes just a Gaussian integral, which you know how to do, right? And after you've done that, you can also integrate out this z naught. Then you get sort of like some integral representation for these d functions in terms of these parameters t. So I will not go through the derivation, but just tell you how it looks like after you implement this strategy. So you have a integral of n ti parameters. And here you have a very simple expression. So in the numerator, you have a delta function constraining the sum of these ti's. And in the denominator, you have something that is bilinear in these t's, ti times tj times xij squared, where xij is xi minus xj. Then the whole thing raised to the power sum of delta I divided by 2. So this is what you get after you do this trick. So if you look at this expression, you find there's actually a very nice property of these d functions. Namely, they satisfy certain differential recursion relations. So if we look at the derivative of these contact Witten diagrams with respect to a certain distance squared, right? So because we have translation invariance, the dependence on these x has to be of the form xi minus xj squared. And if you do this differentiation for the right-hand side, you find the form of this integral representation does not change. You just need to shift your deltas for I and j by 1, then you go back to the same form. So what you will find is that after one derivative, you get back a d function, except that for the i's and j's operator, you change the dimensions by 1. So this gives you a very nice way to compute these D functions. Namely, if you know the form, the function, the explicit functional form of one D function, you can compute infinitely many more by acting with derivatives. So and to make things more explicit, let me give you some examples. Sorry, actually, before I give you the example, I want to point out that these D functions, they also show up in a different context. So in flat space, we can also consider the following type of conformal integrals, which is also defined by some diagram, which I will define more precisely. So we also have propagators, except now the propagators, they are power-like, because this is in a CFT. And this integral corresponds to the sum, the product of some x naught divided, minus x I squared to the delta i's power. And then, so these are the x1, x2, and this is x naught. Then you integrate over x naught in some flat space Rd, where this capital D needs to satisfy the relation that is the sum of all the delta i's. So you can check, for example, by acting on this diagram with a dilatation operation, you can show that only when the total space and dimension is the sum of all the delta i's, this integral is conformally invariant. Now you can use this trick again, right? So we also know how to compute this integral. So the trick is the same. We also use Schwinger parameterization to move the denominator into the exponent. Now everything becomes quadratic, so you know how to integrate out x naught. And then surprisingly, you end up with the exact same integral representation. So actually, so this conformal integral in Rd is actually proportional to this contact weighting diagram up to some numerical factor. Okay, and this relation actually allows us to get some explicit example for these ADS contact weighting diagrams by using results people have already known in the amplitude literature. So let me give you a result, give you an example. Where n equals to 4, so we have 4 points, and all the dimensions equals to 1. That in particular means the space and dimension D is equals to 4. So this is this cross diagram, which you can also do a dual transformation to the variables to write it in terms of the dual variables. This is nothing but a one loop box diagram. So this sort of like position space. This is in momentum space.
When you say T dual, you literally mean do a Fourier transform.
What I meant is essentially you consider these. Yes. Right. Right. So these are these are like x1, x2, x3, and x4, and then you do this transformation. Now these are like momentum variables, and so people from the amplitude community they knew how to compute this diagram things forever. Actually, yeah, so because this diagram is going to show up in the second lecture, so let me just give it a name. Let me call it phi. And here the details are not important. We will come back to that in a bit later. But I just want to show you that this integral can be explicitly evaluated in terms of some quite elementary functions. It involves these polylogs with at most weight 2. So these z and z bars I will discuss a bit more in detail later on, but these are just the conformal cross ratios, which can be defined in terms of this xij squared. So the take-home message here is that if you look at this D1111 contact weighted diagram, it has an explicit form in terms of the cross ratios. Now, using this differential recursion relation, you can compute many more D functions. For example, you can act with x12 squared, right? And this will give you the 2211. So you take one derivative, you get this. And then you can also take another derivative with respect to x34 squared. This gives you the 2222. Also here, you should notice something quite interesting. So I can do this in different ways to go from here to here, right? So I can first do it with respect to, let's say 2, 3, right? So I have D 1, 2, 2, 1, and then I do 3, 4. I get by the same answer. So this gives you some sort of like consistency condition for these recursion relations as well. I will not go into the details, but if you're interested, you can look into. I mean, you can read about it. So this consistency condition actually has something to do with the conformal Yangian invariance. Okay, so that's all I want to say about this contact weighted diagram. So the take-home message is that we know how to compute them, at least for some nice integer dimensions. Now let's look at exchange diagrams. So let me remind you, it has this shape, right? Where you have two integrals to do. You can try to use similar tricks as we use here, Schwinger parameterization and so on, to compute them. But there's a nicer way to do it, which is to try to compute this diagram by solving a differential equation. So let me explain how that works. So the starting point is to look at part of the diagram. So half of the diagram where we only look at y integration. So it's sort of 3-point function where you have 2 points on the boundary and 1 point in the bulk. And then let me call this function A. And here I have 1, 2, and this one, let me call it Z. The point you integrate over is W. So this diagram clearly satisfies conformal symmetry, which means if I act on A with infinitesimal conformal transformations, namely the generators, it should be invariant, right? So I have generators acting on these 3 different points. So I have a generator at 1, generator at 2, and also the generator at Z. So this index I just labels different conformal transformations you can look at. And the action on Z looks slightly different. It's like this curly L. The reason is because so the interpretation is slightly different. So we have conformal symmetry on the boundary, but the conformal symmetry is the same as the ADS isometry. So that's why I made the distinction. Okay, now starting from this invariance property, we can act again with these generators. But first, let's move the last term to the other side. So we have L1 plus L2 acting on A, the same as minus LZ acting on A. But then we can sort of square, we can act again, which squares these generators, right? And I can add minus 1/2, just for conventions. And you realize that on the left-hand side, this corresponds to nothing but this Casimir operators of the conformal group, because I also need to sum over all the I indices. So more precisely, this is a 2-particle Casimir operator, because the generator acts on both 1 and 2. And on the right-hand side, you also know what it is. So because here, I should have mentioned that we are looking at some scalar exchange diagram. So the internal propagator is a scalar field, okay? And the action of LZ squared is nothing but the ADS box operator acting on the Z coordinate, okay? Now we can look at what this means for the exchange weighting diagram. So what this means is okay, so let me first write it down. So we look at the action of the 2-particle Casimir acting on 1 and 2 minus m squared, where m squared is delta times delta minus d. So this is standard mass formula in ADS-CFT, acting on this exchange diagram, and I claim this gives you just the contact weighting diagram we've already discussed. To see why this is true, we can sort of like forget about the second integral and just look at first the 3-point part of the integral, right? So we know that the action of the 2-particle Casimir is the same as box, right? And so it acts on this point. But we see that what is connecting to this point is this internal bulk-to-bulk propagator, which satisfies the equation. Well, it's a green function, right? So to satisfy the equation that this operator acting on this equals to a delta function, right? And so you plug this in, and then you complete the diagram by doing the other integral. So you multiply with 2 more propagators and then do the integral. And this delta function gives you precisely this, right? So it identifies these 2 points. So it's sort of the internal propagator is collapsed, and you have a contact diagram. So this gives you an identity relating these exchange weighting diagrams with contact weighting diagrams. So instead of doing the integral, you can obtain the exchange diagram by solving this differential equation. So let me tell you what the solution looks like. So in general, the solution after you have, so it is not quite obvious from this perspective, but it's more clear if you start from this the sort of three-point part of the integral. You can see this differential equation is actually an ODE. So it really that is essentially because this part of the diagram only depends on one cross ratio. There's only one variable, and ODEs are simple to solve. And after you have solved it, you find that these exchange diagrams can be written in terms of these contact diagrams, which you already know how to compute, with some shifted dimensions. And here you have some powers of x and j just to compensate these shifting the conform dimensions with coefficients which you can explicitly obtain from solving this equation of motion identity. So that is sort of like the punchline of these exchange Witten diagrams. And you can express them in terms of these contact Witten diagrams. Let me also point out some interesting simplifications, which actually will be used in the next lecture. So in general, when you write down the solution in terms of contact Witten diagrams, you find that the sum is infinite. However, there is some simplification if the spectrum of your theory satisfies certain properties. And quite interestingly, these properties are satisfied, say, in 4D n equals 4 CP Mills at strong coupling, or some other models like 6D2,0 theory. So what are these conditions? I'll remind you again, but here, let me just write it down. So essentially, when the sum of external, these two, one side of the diagram, minus the so-called conformal twist of the exchange operator is some even positive integer, or the sum of 3 and 4 minus the exchanged guy is some positive even integer. The sum becomes finite. So this means you can express these exchange Witten diagrams as finitely many of these contact Witten diagrams, these D functions. And we know that these D functions, like D1, this is just only two function, and it remains at most two with the action of the differentiation. So you know, like roughly what this exchange diagram looks like. It is also just some polylog functions. Are there any questions on this point? Okay, so let me just yeah. So also, there's another thing I want to say. So here, what I was trying to explain is basically how to compute these tree-level diagrams in ADS. I talked about these contact diagrams, and then these exchange diagrams, which can be expressed in terms of these contact Witten diagrams. So these will be, I mean, these are the building blocks people used in the literature to honestly compute the holographic correlators. What people basically did is that they start from some effective Lagrangian they write down all the vertices relevant for a certain computation, and then they enumerate all the diagrams, then they compute diagrams one by one, and then they sum up all the diagrams. So next lecture, I will show you there's a smarter way to do this perturbation theory without this whole process. But today, just before I end this lecture, let me also point out that these Witten diagrams, they actually are also useful in a different context. For the so-called, well, they're useful for the analytic conformal bootstrap. Where the idea goes all the way back to Polyakov in the 70s. So these exchange Witten diagrams here actually secretly are the building blocks used by Polyakov in the 70s. So nowadays, like, well, in standard CFT lecture, we will decompose a correlation function into conformal blocks. So the conformal blocks, they form a basis for writing down your correlation function. But there's actually an alternative basis used by Polyakov, which are these essentially these exchange Witten diagrams. So the difference is that if you use conformal blocks, you sort of manifest OPE, but you don't have manifest crossing symmetry. And when you put these two conditions together, you can obtain non-trivial constraints for the data defined in the CFT. Here, the Polyakov idea is sort of the opposite. You start from these exchange diagrams, which have good crossing properties. Yes, I will, yeah. But the interpretation in terms of OPE is less clear. So in this Polyakov approach, you should instead impose that when you decompose them into conformal blocks, all these spurious operators are gone, and this gives you equivalent constraints, but in a different form for this CFT data. So I think this is a good stopping point.
We are 4 minutes early.
Okay.
They ask for questions. Okay, so thanks for a very nice lecture. Questions?
I guess that these Witten diagrams look very natural if you know about the log.
Yes.
Why was Polyakov using these functions? How come they came this? I mean, he was doing this in the 70s, right?
Yeah.
Is there a simple way to see why he was considering the same kinds of functions?
Not really. So because I mean back then there wasn't ideas. So he was actually defining it more like I think it's more similar to like these conformal integrals. He was trying to construct some basis which is has good like crossing property. Yeah.
I see.
But somehow it seems like these objects are not. I mean they're a bit rare. But the thing that he constructed is essentially the same as these Witten diagrams, these exchange Witten diagrams. Like another way to see it is like these contact Witten diagrams. I mentioned that they're exactly the same as these conformal integrals in flat space. So they're not, in a sense, there are not so many objects with these good properties.
Questions? So maybe I can ask one question. So you mentioned Jeffrey Chew's contribution from back in the days. So what was his original motivation to look at Bootstrap?
I think back then, like a local QFT had many problems which people at that time didn't know how to fix.
Yeah.
So he was trying to start from, I mean, different perspective. So he was basically saying that we don't need a Lagrangian, like all the particles that are equally fundamental, and the interaction rules are determined by self-consistency. So
what did he get out of that?
I would say,
You mentioned about Romeson.
yeah, I mean, Romeson mass, he managed to determine from the conditions, but I mean, but you know, like the program is eventually not that successful. People then discover the QCD. So yeah, so the idea like went into like other areas like conformal bootstrap and so on. Yes.
Any other questions? Okay, looks like there are no more questions. So let's take a break. We'll have a coffee break for minutes. So let's thank the lecturer again.
You're coming from England.
Yes, from England. How long is it? I'm
That's what the guy was very. So you're okay with that?
Very good. I'm sitting next to you.
Live here.
Yeah, let's get going with the final session of today, which will be by Sergio.
Thank you. Thank you. So as briefly explained yesterday, today I'll be discussing with you a program in which we can try to better understand the microstates of BPS black holes in the ADS-CFT holographic context. So using quantum field theory and quantum mechanics. So the first half of this talk will be explaining to you the general program, often called the supercharged homology. The latter half I'll be explaining to you one application. It's an application to better understand the microstates of the hairy black holes, the kind of hairy black holes that I explained to you yesterday. So I explained to you, I gave you a little flavor to you at the end of yesterday's talk, how we can understand the black hole states by counting them, by computing its entropy, let's say, by using some protected partition function like indices. Today, the goal is grander. We want to try to understand the nature of the states which actually contribute to this entropy or the indices. So to do this kind of thing, for instance, if you're interested in studying supersymmetric black hole states in ADS5 times S5, we are studying these states in the dual N=4 superconformal field theory, N=4 Yang-Mills theory with large NDH group. This requires to study the system at strong coupling and at very large N. And the thing is that much of the recent progresses about this program, even if we are in the BPS sector, has happened at weak coupling and not too large N. You might think that the standard law is that if you study the sector with supersymmetry, many observables and physical quantities are protected by this symmetry so that you can do a weakly coupled calculation and get some insights about strongly interacting systems. That's only partly true in our example because the number of supersymmetries preserved by the black hole is too small. So the supersymmetric non-renormalization theorem does not hold completely. It only holds partially in a limited sense. So as for this, as for the studies that have been made in this completely opposite situation than the situation you're interested in, I should first give a few remarks about how we should interpret them. Okay? I mean, the fact that most of the studies have been made at finite n, it's more practical. I mean, very detailed practical problem. I mean, conservatively, you can try to understand the studies made so far as a step towards going to larger and larger n. If you don't understand smaller n well, how can you go to a larger n? So you can understand it as a step towards getting to larger n, or hopefully in the near future. If you're more brave, you can try to interpret these finite n heavy operators and heavy microstate constructions as trying to construct the black hole states in very quantum gravity, where the Newton constants are not supposed to be parametrically small. You can understand this situation in two different ways. As for the studies done at recoupling, there are more serious issues. Some of these recoupling BPS states and the cohomologies that I explained to you are partially protected by supersymmetry, especially some of these recoupling states whose contribution to an index doesn't cancel. They are supposed to be protected. At least their spectrum is supposed to be protected all the way to strong coupling. But it is well known by now that some of these recoupled states that I'll explain to you are not protected. Okay, so the situation is quite unclear. Only many of these heavy operators of state constructed so far preserving supersymmetry are those which contribute to the index, so they are sort of believed to be protected, but not all of them. At the very least, one can try to understand these kinds of weak coupling studies as a semi-realistic model for studying black hole microstates. So depending on your rigor, conservativeness, or vagueness, you can understand the program I'll be explaining to you in various different ways. In this program, some important features that I'd like to highlight in the first half of my talk is to find a good mathematical way of distinguishing the black hole states with other states which I collectively call gravitons, the states which are dominating the low energy spectrum of the system. Okay? We already heard of these concepts, I mean, partly in yesterday's talk, like Antal's or Joao's talk. I mean, the important roles are played by trace relations and so on, by the larger matrices. And I'll be trying to explain to you the applications in the latter half of my talk, trying to better understand the hairy black hole microstates, and if time permits, discuss with you a related information problem, black hole information paradoxes. So this is the most technical slide on my talk. It really didn't have to be this technical, but I wanted to phrase the situation concretely in a very specific context. I'll explain to you the problem in the context of N=4 supersymmetry Yang-Mills with SV engaged group. But similar problems can be phrased and studied in much simpler models. So if you feel like you don't really have to follow all these details, I won't even explain the details to you. I hope you just get the skeleton of the structures that I explained to you about this problem. So, sorry. The N=4 super Yang-Mills in N=1 superfield language has 3 chiral multiplets and 1 vector multiplet. It's like the multiplet that we heard in cosmos this morning. So we want to consider a local gauge invariant operators made out of all these fields, vectors and gauginos, scalars and chiralinos, so on. And we want these local operators preserve 1/16 of the 32 supersymmetry of the system. It's the minimally supersymmetric system, supersymmetric operators in this system. Namely, you pick one of the 16 Poincare supercharges, which are just collectively called Q, and another Hermitian conjugate supercharge of it, which is chosen among the conformal supercharge in the so-called radial quantization. And you demand your gauge invariant local operators to be annihilated by both of them. So these operators or states annihilated by Q and Q dagger are saturating the lower bound BPS bound of the energy by its energy being, or the scale dimension of the operator being a linear combination of the R charges and angular momentum. Yesterday I called them Q1, Q2, Q3. Those will be due to the electric charges carried by the black holes. Today I'll just call them R for R charges. Q is spared for supersymmetry. And these are exactly the supersymmetries preserved by the holographically dual black holes in ADS 5 times S5, so which justifies the setup of this problem. So if an operator is annihilated by Q and Q dagger, or Q and Q dagger anticommutator, we use the fact that the supercharge chosen is nilpotent. It's part of the algebra of this system. So this Q and Q dagger are formally behaving, Q are formally behaving like an exterior derivative acting on a differential form. But formally, these BPS states can be regarded as harmonic differential forms. And we use this Hodge theory to make a one-to-one correspondence between the spectrum of these harmonic forms and the cohomology classes with respect to this nilpotent operator, which defines my cohomology problems, meaning that I'm interested in differential forms or local operators, which are closed under the action of this differential operator, this Q operator, identifying the two operators which differ by a Q exact shift. So if you study the spectrum of cohomology classes of this Q, they are in one-to-one correspondence with these BPS states. Yes, please.
Research supercharge. Is that correct? You're doing a topology interesting.
No. Why do you say so? Oh, because they don't have any indices. Oh, they have so they have particular indices. They have R symmetry indices and spin indices. I could have shown that, but I just omitted them and just pulled in Q. They are spinor valued.
You are not twisting the.
Huh? I'm not twisting. I'm not. This is the spinor supercharge. Spin down component and assuming a particular component in our chart. I'm not doing the twisting. Yeah, like that. Sorry if the notation was confusing. It's just schematic notation. Yeah. So what I like to do, this problem can be phrased at arbitrary coupling if you use this quantum supercharge, depending on the Yang-Mills coupling constant, but it's generally difficult to study. All we can do is a study at recoupling. So I'm going to explain to you that. The easiest thing to do is to study local operators in the free theory limit. Super easy to do. All you have to do is to select out a subset of these fields, elementary fields or letters, which are invariant of this Q and Q dagger in the free limit. And those are the subset of these letters. An anti-holomorphic component of the chiral multiplet, the gauge chiralino, some component of gaugino, and a particular component of field strength. And those fields dressed by arbitrary number of holomorphic derivatives, they are BPS letters or BPS elementary fields. Once you identify this BPS elementary field, you form arbitrary gauge invariant composite operators. They are all BPS because in the free limit, the composite operators don't acquire anomalous dimensions. But this, you can easily construct them, but they exhibit features which are too much different from the features of the BPS states in the strong coupling limit. So we have to go one more step beyond that. Okay? You find way too many free BPS operators compared to that you observe in the strong coupling, let's say gravitons, black holes, everything. So, excuse me. So to hope to achieve a better situation, you go one step beyond that. So once you identify the set of free BPS operators, you study how many of them survive to be BPS if you turn on small coupling constant. In particular, if you consider the action of the interacting classical supercharges on the free BPS letters, some of the right-hand side turn out to be non-zero. The typical supersymmetric transformation law in the classical supersymmetric Yang-Mills is that the supersymmetric transform of a letter becomes G Yang-Mill times commutator. So these are some of the non-zero terms if you try to act the interacting Qs on the free BPS letters. So this way, some of the free BPS operators, due to the non-zero right-hand side, turn out to be lifted at the interaction level. And since this classical Q is linear in G Yang-Mills, half loop, the anomalous dimension operator, which you can write in this way, turns out to be one loop, square in G Yang-Mills. So if you study the subset of free BPS operators, which remain to be BPS after turning on G Yang-Mills at half loop, classical supersymmetric transformation, you are leading to study the BPS operators which remain BPS up to one loop order. And this is the question we'd like to study in this talk. Yeah. Things might change, and it has recently been illustrated that things does change for some of them. A few months ago, an example has been found among the one loop BPS states, which gets lifted at the situation. So that's why I've been telling you so many excuses in the previous. Half a year ago, I never wrote anything like that. There's a conjecture that one loop BPS states will remain BPS at all order, and I'll be proceeding with this assumption. Now I have to make more excuse, but I think the problem has been much more exciting. There are many dynamical issues and so on. So yeah, please.
I relate to the question. So here the BPS guys can fail to be BPS when you switch on interactions.
Yes.
What about the trace relations? The trace relations are productive operators, so they're composites. Can you not have divergences that would mean that something that was a trace relation in the free theory is not a trace relation in the interacting theory?
I think if you go to 2 loop or higher, this multiplying quantum operators might be causing that issue. Up to 1 loop, it all boils down to classical questions. So I think that issue could be absent.
But at higher loop, the trace relations themselves could also.
Yeah, because you're multiplying quantum objects in. I agree that things might be answered.
Trace of phi bar, that could certainly appear in a trace relation. That would be, it would have a non-zero short distance singularity.
Yeah, at higher loop, I think your worry might be relevant. Yeah, I'm not really sure about it. Yeah. I think, that might be an issue. Okay. Anyway, this is the question. And as I may have time to illustrate, I mean, many of the studies has been done by assuming that these 1 loop BPS operators, at least their spectrum is protected all the way to strong coupling. And that's certainly true for many operators. Because until recently, mostly I have been paying attention, constructing the operators which are captured by the indices. There's some super conformal index and so on. And they are believed to be protected. But there are some pair of these cohomologies which pair and cancel in and don't appear in the index. And some of them have been shown to be actually lifted at high loop. Yeah. Okay. Any other question about the problem? So what I'd like to emphasize to you first is to explain to you the 2 possible classes of cohomologies or the BPS states. I first like to explain to you what I will be calling gravitons, the BPS states that account for the low energy spectrum in the large L limit. Okay, I'll spend some time to explain that. And these are the cohomologies we have been understanding very well from many decades ago, from the early days of ADS-CFT. So I'll give a practical way of constructing all the graviton operators, graviton cohomologies, and then try to characterize them in a more abstract fashion in the next slide. So construct the representatives of what I call graviton cohomologies. What one first do is to study the cohomologies of operators at a single trace level. You only use 1 trace. Okay? You assume that it's a very big matrix, n by n matrix, and you only use a few letters so that the relation between single trace and multi-trace could be ignored. I mean, it doesn't exist. So at the single trace level, for instance, very simply, for simplicity, you consider the single trace operators of BPS scalars only. And you realize that if these BPS scalars inside the trace is partly anti-symmetrized like that, the location is anti-symmetrized, they can be made Q-exact. Which leads to the fact that if you want to consider non-trivial cohomology representative, you have to completely symmetrize the scalars within the trace. These are nothing but the extremely well-known scalar chiral primaries of single trace cohomologies. Once you get this, the other graviton type cohomologies can be obtained, at least their representatives can be obtained in the following 2-step manner. First of all, to construct the rest of the single trace graviton type cohomologies, you act on this chiral primary, the subset of the superconformal algebras, which commute with the Q and Q dagger that I defined, because I want all my states to be supersymmetric with my Q and Q dagger. That turns out to be this PSU 1/2/3 subset of the full superconformal algebra. So for instance, if you try to start with trace of scalar square and act this generator, you get a lot of descendant operators like that, as well as the conformal descendants. So this way you get the complete set of single trace graviton operators. Then the remaining operators you get by simply multiplying them. You get multi-trace of these, and you get the multi-trace operators, which you morally understand as multi-particle states of gravitons in ADS5 times S5. In the large N and low energy regime, what I told you, I mean, the interpretation as graviton is very precise. So trace number is identified as a particle number. This construction provides the BPS multi-gravitons, single gravitons and multi-gravitons in multi. Now I'd like you to remember the rough structure of this construction and consider them at finite n, not necessarily large n. Or even if the n is very large, I ask you to consider this operator I just explained to you, when the scale dimension of the operator could be quite large. I mean, the number of letters is larger than n. In this case, we cannot really ignore the fact that the matrix size is very large, but I keep calling them graviton cohomologies. First of them, it's quite clear that they are cohomologies. They continue to be Q closed, no matter what the value of n is. Because in the previous slide, when I was ensuring the Q closeness of these operators, I never used the matrix size actually. The Q closeness is ensured, meaning that they will represent some cohomologies. Non-trivial part may be that as a representative of cohomologies, they may be redundant if n is finite or if energy is larger than n. This is because of the trace relation of operators with different trace sizes that Antal and Joao has explained to us yesterday. Because of this relation between multi-trace operators, the list of cohomologies I've listed to you, they're all representing some cohomologies, but they're overcomplete because they're satisfying some relations. And the graviton operators and the large graviton operators satisfying such relations are well known from the ADS5 times S5 gravity dual. They are called giant gravitons. They are the gravity dual of these overcompleteness of the naive count of the graviton states. And the gravity dual requires us to describe this kind of heavy graviton operators in terms of branes rather than particles. So this is very well known. So there's a good reason to still call them graviton, even n is finite or energy is larger than n. Yes. Yes.
Is it the same effectively?
Yes, if you expand it in terms of multi-traces, I mean, I'm caring less about the orthogonality and so on. I'm just caring about whether I got independent operators or not. Yeah. So
that definition is not a determinant relation.
yeah. They enjoy better properties, but I mean, if you just care about linear independence, you can just keep thinking about them as multi-trace operators subject to various relations. And you can try to understand these graviton operators or in the following way. Since I've never used a finite size of the matrix there, you can find a given type of graviton operators, let's say of given shape, at arbitrary values of n, making a given graviton operator into an infinite sequence by changing n. Okay. So since such an operator exists at arbitrary value of n, we call, in the recent literature, people call them monotonous operators. They might be dependent at multi-trace level, but anyway, these operators exist at any values of n. Basically, everything else, apart from these graviton homologies, are what we are mainly interested in to study the black holes. Okay. And if you carefully study the logic of the logic, I never use the trace relation to construct the cohomologies of this graviton type or monoton type. And you can slightly invert the logic. I mean, if you demand that you never use the trace relation to construct the cohomologies, you end up by having the graviton cohomologies I explained to you in the previous slide. That this means that to construct any new cohomologies, these have to be Q-closed by using trace relations at particular n. Okay? Otherwise, it boils, if it's not the case, it boils down to the graviton cohomology. So that led these authors to give the name fortuitous cohomology, fortunate cohomology, to these latter class of operators, which I interpret as you have to be fortunate to use some well-designed trace relation to make it Q-closed. Fortunate operators, okay?
Easier to say.
To me, they sound similar, right? The spirit is not the same, is it? Okay, we can talk. I'm very bad at giving names.
Well, the rhymes. Monotonous and miraculous. So it is two ends.
Okay.
I think because the vast majority of black states are black holes, it's a bit weird to go with which is the best.
Only in the technical sense, because if you have played with trace relations a bit, you'll find yourself extremely fortunate if you have successfully done that.
Volunteer to be a black.
Yeah, so it's a name which will be appealing to a practitioner like me. But physically it makes.
There's some tension between the typical state and the refrigerator.
Okay. Again, emphasizing to you, I'm extremely bad at giving physical objects names, so please bear with me. Okay. Okay. So, I mean, of course, calling all fortuitous states to be black hole states may be a bit overstating, because we don't really know for sure whether there are some states which deserve neither to be called gravitons nor black holes. But in this talk, I mostly call fortuitous states and black hole states and miraculous states as all synonyms. Okay. So normally at this stage, I mean, if it had been a technical talk, I would have explained the examples of constructions of these fortuitous, miraculous black hole states. These are extremely technical. There has been recent progress in the past 3.5 years trying to construct an example of such black hole type operators. It's an art of playing with trace relations and so on. I mean, we have constructed many examples, and if we cannot construct these representatives, at least their spectrum has been studied in various cases, but mostly with small n's, n equal 2, 3, and 4, and so on. So there are some lists, and many examples are playing important roles to get better intuition on the physics, but I'll not explain them all to you. I mean, I can spend lots and lots of time giving you examples, how trace relation makes it Q closed or not, but it's too technical, so I'll just skip. I mean, I won't even let you to see a single example of that, so please forgive me. I'll be discussing some physics of these black hole type operators in the latter half of my talk from now. The operators examples that I didn't explain to you today were importantly used to confirm and test the properties of these black hole type operators that I will be explaining to you from now. So yeah. It's a side comment about a subset of one loop BPS operators which were confirmed to be lifted at full loop order, but I'll skip explaining this. The remaining time, I'll spend some time with you discussing about some application of this cohomology formalism to better understand first what's called what we can call the hairy BPS black hole microstates, the kind of black holes I discussed with you yesterday. And the complementary notion of hairy black hole microstates is a no-hair theory. The first case is where the hair is allowed to dress a black hole. The second case is where hair is not allowed to dress a black hole. So I'll be discussing to you a quantum microstate version of the hairy black holes and the no-hair theory in the remaining time. So to discuss this, I want to start by reminding you a very basic property of this cohomology. You know, the action of supercharge on an operator, composite operator, at least if it's a classical supercharge, it acts on basic elementary fields one by one. Okay? So due to this fact, the action of Q is satisfying a Leibniz rule. And the Q acts on individual letter one by one, and you add all the terms, like you act derivative on some functions. Due to this fact, if two local operators are representing a cohomology, I mean being Q closed individually, product of them are also automatically representing a cohomology because of the Leibniz rule. Q acting on this composite is Q acting on O1 plus Q acting on O2, but individually they are separately Q closed. The product represents a cohomology also. And this fact played an important role in many places. I'd like to discuss this kind of product cohomologies to discuss microstates for hairy black hole. Important thing is that at least one of these operators we want to be large and heavy, describing black hole microstates. So in such cases, it is unclear if the product is a non-trivial, representing a non-trivial cohomology or not. Okay? if the product remains not Q-exact by using any trace relations of large operators, they will remain to be a non-trivial homology. It turns out that in some cases, the multiplication of these large operators can be Q-exact by using trace relations, in which case the product homology is trivial. And using this structure and studying lots of examples that I didn't really show to you, we are led to suggest microstates of a BPS hairy black hole homology, microstates for just the BPS hairy black hole. And this kind of microstates will be for the gray galaxy type black holes that I explained to you yesterday. So yesterday you recall that for spinning black holes, there were first kind of hairy black holes where the hairs are consisting of small particles just fastly rotating outside the event horizon of the black hole. We call that a gray galaxy type black hole. The second type of black hole was the charged hairy black holes, which are a bit exotic. There were some large D-brain-like hairs wrapping the whole black holes, providing a charged hair. They are not really light operators. They are already giant graviton-like operators. We also have a suggestion for this exotic heavy hairy black hole homologies. It's in a paper that I wrote with Robert and many other collaborators. I will not discuss that for the sake of saving time. I'll explain to you this great galaxy type hairy black hole homologies using the product homology representative. So consider what I will call a core black hole microstate operator, H for heavy, and a light operator, L. It can be one of the small graviton operators. Okay? This is the core heavy operator and a light operator, and consider a product of them. Okay? They might be trivial or they might be non-trivial. We'd like to say that the product, if they are non-trivial, a light operator is an allowed hair which is allowed to dress this heavy particle, heavy black hole state. On the other hand, if they turn out to be Q-exact by trace relation, L is not allowed to dress as H, at least in the BPS sector as a homology. We'd like to suggest this as a quantum microstate version of a no-hair theorem between these heavy and light operators. By studying concrete examples, we'll find both appealing features of these suggestions and some odd features of these suggestions, both of which I'll discuss with you today. Let me first explain to you some appealing features of this suggestion. I mean, these appealing features actually led us to suggest this. And let us roughly discuss what we expect from gravity by this fastly rotating hair outside the black hole. And we consider the supersymmetric version of that. Okay? Recall that the gray galaxy type black hole hairs that we discussed in the previous talk consist of fast rotating particles far away from the black hole, which provides a parametric separation, weakly interacting pictures to construct the approximate configuration. But more generally, we like to discuss, what kind of rotating particles can be staying outside the black horizon, providing a hair. For very simplicity, let us consider the classical probe particle, okay? Making some classical motion around the black hole. And we like to study the BPS orbit of this probe particle in a BPS black hole background. It turns out that by studying this BPS supersymmetric condition, the particle will have to make a circular orbit. And the radius of this orbit is proportional to the angular momentum that the particle carries. And for this particle orbit to stay outside the event horizon to be a legitimate candidate for the hair, it turns out that the angular momentum carried by this probe particle should be larger than a lower bound threshold, where the threshold J naught is set by the size of the background black hole. Okay? So it's quite natural, right? The larger the J is, the larger the radius will be. The smaller the J is, the radius will shrink. J equal to J0 is exactly the value at which the orbit is on the horizon. Okay? So this is providing a lower bound. And this is roughly what we would expect for a particle to be the hair of a background black hole. Okay? J being larger than certain critical value. And studies of this product homology, heavy times light, in the quantum theory, like the n equal 4 Yang-Mills, with some known H's and a selection of light graviton operators show extremely similar features. Okay? If the light operator doesn't carry large enough spin, for instance, not having large number of derivatives, we find many examples in which this product becomes trivial, Q-exact by trace relation. But if the operator carries sufficiently large spin, it turns out to be, in many cases we have checked, that they are not Q-exact. In which case we'd like to interpret that as a no-hair theorem. In the latter case, we'd like to interpret as a hairy black hole state. We have never studied, confirmed this kind of phenomena comprehensively. First of all, because we only know a handful of H's, not thoroughly. But whenever we could check, we find a phenomena that sort of supports roughly what we expect from gravity. Light operators with large spin multiply. Large operators with small spin or no spin multiply, and often they become Q-exact. Okay? So it sounds somewhat natural and consistent looking with what we expect from gravity. But if you take a detailed look, this is very different from what we know about the hairy black holes or no-hair theorem from the gravity side. For instance, let us discuss the no-hair theorem side of the two phenomena. What gravity says, what classical gravity says, is that if you are given a light operator, or if you're given the gravity dual field for the light operator, if a black hole's, gravity calculation says a no-hair theorem, it means that a hair is disallowed for this field per given black hole solution, meaning that the no-hair theorem is stated per ensemble of heavy operators, right? However, the suggestion that we made for the no-hair theorem is quantum and at the microstate level, so it's too much detailed than what classical gravity's no-hair theorem says. So if a black hole says that a mode is not an allowed hair for given ensemble, what could be the fate of our quantum proposed no-hair theory? We cannot make a comprehensive test of this in any Poisson mirrors. As I said, at large fixed charges, to answer this kind of question, we'll have to construct the full set of heavy operators at these fixed charges, but we are far from that stage. But just make a statement about two possible scenarios of the relation between the two no-hair theorems. Okay? The first extreme scenario, which I think is quite unlikely, is that when a classical gravity states that a given mode is not a hair, first extreme scenario possible is that for every entry of this ensemble, H times L will be Q-exact for all H's. Okay? So that the classical no-hair theorem uplifts to a complete quantum no-hair theorem at the microstate level. Logical possibility, it sounds, although it sounds quite unnatural and very difficult to be achieved. Okay? The second more natural scenario could be, even if the classical no-hair theorem on gravity says that this ensemble disallows this light mode as being a hair, in the full quantum studies, there might be a fraction of H's in this ensemble, which yields non-trivial product homologies. Okay? Small fraction, presumably. So if this second scenario is the case, it might be a fine-grained quantum violation of the classical no-hair theory. I cannot really judge which is the case by constructing H and testing them, but in the remaining part of the talk, 2 or 3 slides left, I'll show that the first scenario is not just sounding unnatural. I'll try to argue that, after my preliminary studies, I'll try to argue that the first scenario is actually incompatible with the resolution of black hole information paradox that people have been putting in the recent decades, which presumably is favoring the second scenario, that there should be a subtle fine-grained violation of the classical no-hair theory if you want to promote it at the level of quantum microstate level.
This observations.
Yeah.
So how did you find that in practice? Is it more of a brute force thing, or is there some analytic thing to see? Or
This one?
Yeah.
Yeah, you probably know the answer, but we first noticed this by computing the index of these heavy operators, fortuitous operators. You know, index for all operators is easier to compute. We computed the index over these gravitons, subtracted them, and then we found the following interesting features. You know, the lowest term in this fortuitous operator could be accounted for by certain explicitly constructed homology. Then, if you look at the higher order terms in the index, I mean, naively you thought that these product operators with certain light operators could have appeared, but they keep disappearing in the index, which led us to a suspicion that these heavy times light operators, many of them will actually not exist because they don't appear in the index. Motivated by them, it was actually in the old SU2 theory. We actually multiplied simplest light operator, like trace scalar square, onto the lightest heavy operators, and actually showed that by extensively using SU2 trace relation, they can be very non-trivially rewritten to exact.
That is very that's not obvious.
Yeah, one of my collaborators, Sunjin Che, had to grind all his time and effort to, you know, if you have a fixed heavy and fixed light operator, if it's gonna be Q exact, there can be a complete basis for that, right? He wrote down all the complete basis and showed that if any linear combination accounts for this. So it's a brute force calculation. Clever way of doing that? I'll say no. I'll say no.
This relies more on the property of the light than the heavy, or does it also depend on the heavy?
Of course, it depends on the heavy because only then you can use trace relation. You know, you have to have many letters, right? I mean, what makes this product heavy is the heavy part.
It's such a sensitive. Does it need to be large, or is it more detailed?
That I'm not sure. You know, the necessary condition for being able to use trace relation is provided by heavy. Of course, the detailed form of light is really important, as I said, large spin or small spin. Not sure how sensitive it depends on heavy. Yeah. If I got some feeling about the heavy operator dependence, I could have given a better answer than just phrasing a scenario. But you know, really concrete studies has been carried out by only one heavy operator at SU2, and everything else is an indirect evidence. So yeah, I don't.
It does for all.
There are signs of that. Yeah, there are signs of that. Yeah, I agree that it depends more on light. Probably meaning that in the second scenario, the heavy operator violating this theorem is of just small fraction or something. But yeah. Currently, my feeling that it depends more sensitively on light. Any other question about this? Yeah, it's just two scenarios, just imagining. So having these two scenarios in mind, in the remaining, I have time, right? Yeah. I have 2 slides and conclusions, 2 more slides and conclusions. In the remaining time, having these 2 scenarios in mind, classical and the relation between classical and quantum no-hair theorem I proposed, I'll be discussing a very famous black hole information paradox. I'll be discussing an information paradox proposed by Juan Mandelstam 24 years ago. It's about the computation of a 2-point function of some light operators in the black hole background. Okay? So it's a cartoon. Cylinder is again ADS. This black one is a black hole. This 2-point function is defined by inserting 2 operators at the boundary of ADS. So roughly, you create a light particle here, wait for a while, try to reabsorb it. Okay? And this light operator is chosen in classical gravity so that the bulk field conjugate, the bulk field dual to it, is satisfying a no-hair theorem in this background. Technically meaning that the quasi-normal mode of this bulk field has a negative imaginary part, so the quasi-normal mode will absorb. So since you create a particle and wait for a longer time, this particle is more and more likely to be absorbed, or the wave is more and more be absorbed by a black hole. So the classical gravity prediction for this two-point function is that if you wait for long time separation, the amplitude for recapturing this particle at later time will be vanishing indefinitely. So this is a prediction directly related to the no-hair theorem of this mode. This is argued to be contradictory to what unitary quantum mechanics says about the same observable. We should view this in quantum mechanics by creating this particle as perturbing a system which can be roughly described as a thermal system. So this mode being absorbed by the black hole roughly means that the system is getting thermalized, which is roughly correct. But if you consider the large but finite size of this system, like parameterized by black hole entropy, for instance, unitary quantum mechanics say that the perturbation made can never be completely forgotten. Typically, this two-point function asymptotically may be suppressed to be very small value, but non-zero still, suppressed by the large size of the system, like entropy, but never zero. In exceptional cases, peculiar cases like BPS black hole background, the suppressed value is less severe. In some cases, it's known to be suppressed by power law of the size of the system. But anyway, the quantum mechanics is saying that the asymptotic value is never being indefinitely small. And this is Mandelstam's version of the information paradox. Okay? And I wanted to study this example, having in mind the two scenarios of my quantum no-hair theorem. I want to mimic this kind of calculation in quantum mechanics by picking this light operator to be a BPS operator in my sense, and considering it in the microcanonical ensemble of heavy BPS operator. And try to mimic the calculation of two-point function in the black hole ensemble background. Okay. So I'm going to compute, not compute, but study the structure of this observable when T2 and T1 become very large. So for instance, I'm going to study when T2 is going to be plus infinity, T1 goes to minus infinity. So these two are on top of each other. And when heavy and light are on top of each other, if they are following the first scenario, all of them will be Q-exact, sort of trivializing things, right? So I'm going to study this structure of these observables. And assuming that the first scenario is true, meaning that all the entries of the heavy ensemble satisfy this quantum microstate version of the no-hair theorem, I managed to argue that if you assume this kind of first scenario, I managed to argue that the average two-point function asymptotically vanishes indefinitely, thereby apparently seeming to lead to a paradoxical, nonsense conclusion that quantum mechanics doesn't seem to resolve the information paradox at all. Presumably, this implies that the original assumption I made is wrong, and meaning that a fraction of heavy operators, small fraction presumably, should be violating this strong version of quantum no-hair theorem. Okay? And I'm trying to better understand these days how many fractions of them could be violating the quantum no-hair theorem, and how they can be contributing to the non-zero value of the two-point function. I feel that there's no hope for studying them in homology problem of n equal 4 Yang-Mills, because we don't even know the full list of heavy operators in an ensemble. So hopefully we could be able to make a more concrete studies in a simpler toy model and so on. And this is the problem that I'm studying nowadays with many of my colleagues these days. So just to conclude, in the first half of my talk, I tried to explain to you a general program of trying to understand the supersymmetric black hole microstate. Despite lots of shortcomings, not yet being able to go to very large N and having to study that recoupling, I think this program is quite interesting, at least giving some qualitative or semi-quantitative lessons. The second half of this talk, I try to explain to you a representative of a hairy BPS black hole microstate from these cohomology approaches using the product representatives. And just to give you a reference and complete feelings, the other type of black hole hairs, more exotic brain type hairs, have been studied in this paper roughly 1 year ago, written with Robert and many other collaborators. but the situation is less clear compared to the first class of hairs that I explained to you today. Okay? And I discussed with you some problems I'm thinking about the black hole information paradoxes. I think in this kind of cohomology setup, we may be able to study other interesting questions on the black hole, quantum black hole physics, if it can be modeled or phrased in the BPS or near BPS context. Okay? So something like the BPS chaos has been studied by these authors some years ago. And many studies are being made with simpler toy models because n equal 4 Yang-Mills, it's crystal clear, well-defined problem, at least in decoupling. But you know, these combinatorics and so on turns out to be utterly difficult, at least so far. So many toy models are being studied. Or not really toy models, like some vector models are in some sense technically easier than the large and matrix theories. And it has reasonably interesting holographic gravity dual. So next week in my last talk, I'm allowed to be technical, so I'll be talking about this topic probably. Yeah. And even for the n equal 4 Yang-Mills theory, you know, so far we have been trying to construct exact classical Q cohomologies and so on. But hopefully, I've been discussing with many people, including Roberts, in various different setups. It'll be interesting to make, we never use large N anywhere to do this construction of cohomologies. So can we use large N to do some approximate calculations of cohomology? At first sight, it may sound nonsense, because being BPS or not is an exact question. It's BPS or not. Nearly BPS means non-BPS. So if any of the approximate large N methods would be available to construct approximate cohomologies, presumably you'll be getting either truly BPS states or near BPS state, which still will be good, I think. So we have many rough ideas, but trying to make these ideas more concrete, I think it will be very interesting. So with that said, I'll finish here. Thank you very much.
Information paradox. That is same calculation generalizes to something like 24
Yeah, very similar.
But there it seems like so it's the fact that it remains constant.
Yeah, it's damped, but it has a plateau. Yeah, yeah.
That is generally given the fact that you're considering some canonical also which is discrete. So the fact that
you can also do it in micro-canonical version. There's a micro-canonical version of spectral.
Okay, but yeah, but what I'm saying is, it's mainly, it's mainly because you have discrete steps.
That's right, yes.
But now you're just computing a heavy light, right? It's a one pure state. So
No. I'm summing over the ensemble of heavies.
Oh.
Yeah. And the thing is that, well, the operators themselves are heavy, but since it's BPS, they're having exactly the same energy, heavy itself. If you multiply them two of them, if they are non-trivial, they will remain BPS. If they are Q-exact, it means that they're trivial in the cohomology in the BPS sector. But physically, it actually means that when two of them multiply to be Q-exact, it means that they live to non-BPS sector. And then the energy level splits, degeneracy splits, and a lot of, complicated spectral structures are expected to show up, and discrete spectrum. And when I was showing that if the first scenario holds, I managed to argue that the asymptotic value vanishes. I used also these discrete natures and yes, so yeah.
If you have perfect R charge concentration in a theory for the fortuitous states.
Perfect means
every fortuitous state occurs at one value.
Finite. At finite end.
At finite.
Okay.
Yeah. Would that imply that you definitely have scenario one?
I think so. Yes. Because then the black holes will be absolutely obeying on R charge concentration, but the gravitons are not. So multiplying graviton will go away from this concentration point. Yes.
Now, in this, is they perfect?
They are not perfect.
Oh, it's not perfect.
Because if you consider large but finite, then it's not concentrated on codimension one surface. They're spread. like n equal to 9, Chiming and Yiming have done. You cannot really see the sharp line, I think. There should be a spread of order 1, I think. Yeah.
And then would you be suggesting that in a theory with perfect R-charge concentration, you cannot resolve information loss paradox?
That seems to be my apparent conclusion. Yeah. But in simple toy model studies like supersymmetric SYK, if I follow what they did, it's clearly a large and approximate notion. There's a width. Definitely there's a width in the way they argued it in various ways. They show some large n Schrödinger Dyson equation and finding some super conformal point. That's a large n study, so they find a curve. But another way of studying that is they try to find, using the randomness of the action of supercharging, they try to find, what should I say? Okay, so I should say this. They try to find the values of charges where let's say the index counting the leading entropy is concentrated. Definitely there's a Gaussian width. Yeah. The index is not concentrated at just one point, but it just damps quickly. Yeah.
When you talk about yes, states and large n, that somehow means that the amount of dimensions plus power.
I guess inverse power of n. Yes. I'm imagining that one. Yeah.
There are such examples, but at recoupling, there's some suppression in. I always forget. I mean, Misha Bocuse have studied some large operators, which is weakly anomalous at 2-loop level or something. So it has some Jiang-Mill factor, but it's suppressed by some large. I don't think it's n. I think it's the inverse size of the operator. Yeah.
Okay, any final questions? Michelle? Otherwise, let's thank them again. And announcements is the shuttle for